Okay, welcome everybody to this morning session, the most important day of the meeting because of the social dinner tonight. There are two announcements that I have to make. This afternoon, so there are two important announcements. In the afternoon, right before the coffee break, at the place where the coffee break takes place, I don't know exactly where, but in the neighborhood there, we will make the conference picture.
So we will live together from here.
Yeah.
Okay, all the group together.
Okay, so that is the first thing. And then a second thing, the social dinner tonight. On the program, it was announced to take place starting 8:30 in the evening. It will be, for organizatorial reasons, 8:15. So you have to be 15 minutes earlier there. And it takes place in the theater next to the...
So all details are on the homepage.
Okay.
Maybe you should have it in your folder.
Okay. So, and I was told it is the same place where the conference dinner took place 20 years ago.
Yes.
For those who were already there. Okay, then it is my pleasure to announce the first speaker of this morning, Tomasz Brzezinski from the University of Swansea and from the University of Bialystok. He will talk about Lie algebra fibered affine spaces. Please, Tomasz.
Thank you, Seth. Right, so first of all, thank you very much to Claudia and Alessandro for invitation and for organizing this wonderful conference. So my talk will not touch Hopf algebras, so I will not mention Hopf algebras. No, I already mentioned Hopf algebras, so I will not mention them anymore, perhaps. Or monoidal categories and so on. So it's a slightly different topic, but it's a topic I say a sort of bee in my bonnet to the idea to develop well, the sort of algebraic structures where there are no distinguished points, no zeros. So which essentially means replacing the linear structures that we normally deal with, or additive structures, with something which is affine. Okay? So I will illustrate this idea on the example of Lie algebras. So Lie brackets, how you define Lie brackets when you don't have additive structure, you just have the affine structure. And the talk is essentially based on the second of the paper written with Ryszard Andruszkiewicz, no relation to Nicolas, I guess. And my student in Białystok, Krzysztof Radziszewski, and also partly, so the theory was developed together with my student in Swansea, James Papworth. Okay, so one can state the sort of philosophical principle that I will apply to these ideas, and this is called this affinization principle. So the affine spaces and all the algebraic structures that somehow do not, based on the same idea as affine space, are defined with no reference to vector spaces or no reference to additive structures or no reference to specified points or elements. Now, choosing a point in an affine space determines a linear structure. Okay, so if you think about a affine space, it's a vector space with no zero, one can say, but if you specify a zero, then you have back your vector space. And any affine map, so any morphism in this category should be uniquely linearized to a linear map between those vector spaces. So you specify a point in one affine space, specifying the point in another. You have a affine map between those affine spaces. But this map should be in a unique way linearizable to a linear map. And a good algebraic structure is the one that's defined on the affine space. But when you linearize it, you get the well-known additive structure. And as I said, I will illustrate it with the example. Is it a real alarm or is it just a test? Test. Okay. Right. Okay. So, I haven't said anything fiery, yet. I hope I didn't start this fire. Right. So the first step is to define a affine space without reference to additive structure. So traditionally, an affine space is defined in relation to a vector space.
Probably somebody inside the elevator.
Okay, so, so you can say that an affine space is a set on which a vector space, specified vector space, acts freely and transitively. So there is an action of a vector space. But if you can combine the action of a vector space or with on the points into a Turner operation. So whenever you have an affine space, you can take 3 points. You can take 1 point and then, okay, I shouldn't press, but anyway. You can take 1 point and the vector between the second and the third, and this combines in the Turner operation, which is fully defined on an affine space. So it's an internal operation, but Turner operation on an affine space. And there is also an external action or external operation, just like this multiplication by scalars, which you just can visualize in that way. Again, it doesn't involve, I mean, I'm using traditional formulation of an affine space, so there are vectors here, but you can extract the information just from the purely by looking at what properties of those two operations have, the internal Turner operation and external one. So the first, this internal Turner operation is something which is known as an abelian heap. So it's already 100 years old. It was introduced in 1924 by Prefer. What is a heap? I will not give a formal definition, but you should think about, you can always describe it in that way, that you have an additive structure. And if you have an abelian group, and rather than thinking about addition, you think about this combination of subtraction and addition, A minus B plus C. That's exactly, you extract the axioms from the properties of this operation. And then you require for your affine space, so it's an abelian heap with an F action, which takes one scalar and 2 elements of the space, and then the axioms can be again extracted from. I will not write them down explicitly. If you are interested, you can look at the recent paper of myself and Paulo Saraco and Simon Bras and Bernard Rybowowicz, where we formulate affine space. It's something completely known in a way, but it's not very widely known. But it's not a new ingredient in the whole theory, that you can formulate the notion of an affine space without the reference to vector spaces. And the homomorphism, so you think about it as in the universal algebra setup, so homomorphisms are functions which preserve both structures. I will come back to homomorphisms for a second. Okay, so affine spaces are good affinizations of vector spaces in the sense that there's a general property of a heap that if you fix one element, and then you can reduce the Turner operation to a binary operation. So think about this, if you start with an abelian group, think about this O there as a zero of your abelian group, and you recover the A plus B. right? So this A is always an abelian group. If you have a heap, it will be an abelian heap. You will get an abelian group, non-abelian heap, which is also where they exist. You will have non-abelian group. Now, if you then look at this action with we call this element here under the triangle a base. So at the base O, at the same base as the same element as here, this makes a vector space. What's more, so this is sometimes called the tangent space, tangent vector space at point O. And what's more, up to isomorphism, it doesn't matter which point you will take, you will get isomorphic vector spaces. Okay, so how do you get the vectors then? Okay, so going back, you have a vector, it's just the Turner operation OAB, and that's, vectors sometimes in a fine setup are written as the difference. And the action, if you work out what is the action in terms of the multiplication by scalars in the vector space A sub O, then what you get is a barycentric combination. Okay, so the coefficients, the scalars add up to 1. And affine transformation, so I mentioned it's a morphism of heaps. Okay, so it preserves both structures in an obvious way. And there is a corresponding linear transformation, the unique one, which is if you can write it in this Turner way, but if you calculate everything in the group corresponding to OB, then this is the formula, f of A minus a constant. And every affine transformation is of that form. It's a linear part and a constant part. Okay? So in this way, you recover the standard definition of an affine space in the correspondence with vector spaces. But to start with, I didn't specify a vector space. It's just I delivered it. Okay, so the next step is how you define Lie brackets on the structure like this, on an affine space, without mentioning 0. Okay, so in the first think about it might be, well, it's not quite possible, because how do you define the anti-symmetry property, or how do you formulate the Jacobi identity? So here are the formulae. So what you do is, if you in the places where you would, so everything is written in the ternary operation. You can think about this. Maybe I should write it in the binary setup. Somehow we are more used to binary forms. Okay, so whenever you would have a 0 in the axioms of a Lie algebra, Lie bracket, you just put the bracket with the same element. Okay, so there is the first equation here, whether written in the abstract setup or in the binary setup, then this corresponds to the anti-symmetry of the Lie bracket. And this corresponds, so if you neglect the brackets where there are repeated letters, then you just get the usual cyclic condition, the Jacobi identity. Okay, this looks quite complicated first if you think about it, but on the other hand, it's natural in the sense that nothing here depends on the choice or order of, well, the choice of the elements A, B, C, and so on. So, and there is no special element here. Okay, there's no element is distinguished. Okay, so such a structure is called a Lie algebra. So that's a name which was introduced by 3 people from Warsaw, Grabowska, and Urbański in 2003. But they defined, so they were interested in the formulation, it's a sort of program of formulating analytical mechanics without an observer, without a specified frame of reference. And this means without using the 0 in your vector space, so formulating things in the affine way. But in a way, they cheated, because to formulate the axioms of a Lie, call it algebra, they assume that the Lie bracket takes values in a vector space. So if it takes a values in vector space, then it means that, well, you can say quite clearly what you mean by anti-symmetry, or the, well, Jacobi identity is slightly more involved, but still you can write it up. Okay, so I should say that this map, this bracket, is by affine.
So in the middle equation, we have 5 terms in the angular brackets. Before there were only 3.
In the middle equation, what?
The Jacobi identity in the...
Well, there are 6 terms if you count both sides, right?
Yeah,
Yeah, but
but the internal operation had only 3 arguments before.
yes.
And now the middle one is 5.
Yes, because it's a, okay, the 3 arguments. So what I mean by, so maybe I should have explained it, that the axiom of the affine heap means that you can place the brackets whichever way you want. So I could place them like that, or like that, or in the middle as well for the abelian case. So just as we don't write brackets in the associative case in between the binary operations, that's the meaning of this. Okay, so you think about it, one bracket here, and then bracket it with the 2 terms here. Okay, I should have explained. Thank you, York. Right. Now, one can ask, so probably I mentioned homomorphism, but the definition of a homomorphism is trivial in a way, so obvious. So it's a map between affine spaces which preserves the bracket. Okay, so as I mentioned, this work of Grabowska, Grabowski, and Turbański, so when you can recover their definition if I assume that your operation is idempotent. Okay, so their definition corresponds to the idempotent situation. Here we don't need to, well, this definition does not require the bracket to be idempotent. Right, so it's a complicated definition, but is it a good definition? We claim that they are. It's a good definition of a Lie algebra in the sense of the good affinization principle, because if I specify any element, then of course I have an underlying vector space. Then there is a unique way I can linearize or bilinearize the brackets. So I am removing the constant terms, right? And it's one argument, it's second argument, and then removing twice, meaning minus 2 times, so there is a plus, the constant term on both arguments. So it's a unique linear map in this vector space defined at the base O, which corresponds to the bi-affine bracket. And this satisfies the usual axioms of a Lie algebra. Okay, so that's one good thing. Okay, if you linearize a Lie algebra homomorphism, then you get a usual Lie algebra homomorphism. So again, it works on the level of homomorphism as well. And it doesn't depend up to isomorphism, it doesn't depend on the choice of your base element. So you can think about it, and that's how we think about it. I mentioned in the title, it's not quite formal, there's a fibration. It's a sort of, at each point you have in this affine space, you have a fiber which has a Lie bracket on it. Okay, you pick the tangent space, tangent vector space, at each point has a Lie bracket on it. So it's a Lie algebra in the usual sense, linear sense. Okay, and I will denote it perhaps as TOA.
Excuse me?
Yes?
What would be a bad affinization?
Well, so it's a good in the quotation marks, right? So it's a...
So bad in quotation.
If I call something that's an affinization of a Lie algebra, but I didn't get a Lie algebra back by the taking to the linear situation, then I would say, well, something not quite right. Okay, so
something which is not good.
which is well, yeah. And also, perhaps I should also mention about this name, which I don't like, algebra, but unfortunately, affine Lie algebras are already used. And they mean completely, they mean usual Lie algebras, but infinite dimensional ones, a class of them. So they coined, this comes from Grabowski and Urbański, they coined the term algebra. Right, so let's look at an example which immediately illustrates, or it will illustrate that there are plenty of Lie algebra structures on an affine space with isomorphic, while on the tangent spaces you will have the same Lie algebra structure. Okay, so if you take an affine space and a scalar and you just look at this barycentric combination, the definition like that, then it satisfies the axioms of a Lie bracket on A. And if dimension of A is at least 1, okay, so you have at least a line in a space, then different zetas will give non-isomorphic Lie algebras. But if you think about the one-dimensional case as an extreme, okay, on a one-dimensional vector space, there is only one Lie algebra structure, not even up to an isomorphism. It's just one, okay, the unique one, the abelian Lie algebra structure. And here you have, well, as many as there are elements in your field. So it's quite a rich structure. Okay, and so in each case, what you will get when you look at the Lie bracket corresponding to this on the tangent space, vector space, and linear map or bilinear map, you will get a abelian Lie algebra. Okay, so the next step is we start with a Lie algebra, something which is quite abstract and not perhaps easy to handle if you see it for the first time. But at each, when we specify, we have a Lie algebra. If we specify a point. How about going in the opposite direction? You start with a Lie algebra and ask what structures you have to put on your Lie algebra to cook up on the same vector space on which now you think as an affine space to cook up a Lie algebra structure. Okay, so it turns out that the conditions are surprisingly natural, I would say. So let's start with a Lie algebra and we take two linear maps from G to G, endomorphism, and an element. And we can view G as an affine space in the, using the barycentric combination of vectors, and then we define out of the Lie bracket, we correct it with two linear terms, which correspond precisely to putting 0 in one argument, putting 0 in the other argument, and putting 0 in both arguments. So we write, in a way, most general bi-affine map corresponding to the Lie bracket. And then we discover that this is a Lie algebra if and only if, no conditions on S, but lambda, delta satisfy this derivation property. Okay, this condition here, okay, so it's appeared and was studied in 2000. Okay, so I should say that for all, if you look at the tangent, then so you build this structure without the 0, then you select whatever 0 you like, whatever element is a 0, then we get a Lie algebra which is isomorphic to the one we started with. Okay, so this condition, which I will probably repeat. Okay, so which I repeat again. This condition is known as a generalized derivation condition in the terminology of Legel and Lax from 2000. It's a special kind of generalized derivation, so they call a map delta a generalized derivation if there is a lambda and, say, mu satisfying this condition. There are lambda and mu. Here in this mu, the second one on the left-hand side is the same as lambda. But those derivations were studied, and they have interesting properties. So, for example, this condition implies that if you take a difference between lambda and delta, then this map kappa satisfies this property that a kappa of A is equal to 0 And this means that kappa belongs to something which is called quasi-centroid of the Lie algebra G. Again, it was studied by Leger and Lax and Burde, Dietrich Burde later on. And there are some interesting things about this, and this goes back to really the book on Lie algebras by Jacobson, that, well, you can ask when delta is a genuine derivation, right? When it's a genuine derivation. And this happens when kappa is an element of what is known as centroid of a Lie algebra. So if you look at the Jacobson book, and I think it's chapter 10, he discusses, for classification of simple Lie algebras, he discusses centroids. It has some theorems about centroids, and that's the condition for kappa to be an element in a centroid. Okay, so of course, centroid does include quasi-centroid, right? Because if I put A and B equal to the same element, I will have 0 on the left-hand side and A kappa of A on the right-hand side. And there are no restrictions on S, which I've already noted. Okay, so then you say, well, we can use this as a sort of classification tool of the algebra. So we ask what are the isomorphous classes. And again, the conditions are quite natural. So what you have, the Lie algebras corresponding to these two different data are isomorphic if and only if. Well, there is, if you think about it, there is some first cohomology group involved here because it's up to inner derivation by an element. Okay, so we are searching for Q and an isomorphism of Lie algebras, psi, and these are the conditions that you get. And actually, in the simple case, you can read quite a lot out of these conditions, and I will explain it on the next slide. We can fully classify in the simple and finite dimensional case of an algebraically closed fields of characteristic 0. So Leger and Lax show that in this case, the quasi-centroid is actually equal to centroid. Okay, so hence delta is a derivation, because this difference between lambda and delta is in centroid if and only if delta itself is a genuine derivation. Okay, so if you spell out what does it mean that kappa belongs to the centroid, it means that it intertwines the adjoint representation. But then field is was algebraically closed, so we have Schur's lemma, and we immediately learn that kappa must be a multiple of the identity. Okay, so not a lot, not many. We don't have much freedom on the choice of kappa. Okay, so it's quite restrictive. Now, but this is a simple Lie algebra, so all derivations are inner, and up to isomorphism, we can always choose Q in such a way that it cancels delta. So up to isomorphism, delta will be 0. And out of this complicated formula, we can just write very simple formulation that up to isomorphism, AB, the bracket on an affine space with the fiber, the simple fiber, finite dimensional fiber is just the Lie algebra plus this linear correction gamma B and the constant. Right, but this, so far, I didn't take into account the automorphisms of the Lie algebra G. Okay, so then you can study what the automorphisms are in the particular cases, and again, it's already, it's well known, and then you can work out a bit more, so I think I will give this the full classification up to isomorphism when we have SL2C as a fiber. Okay, so if I use the Chevrolet basis, then as is well known, any automorphism of SL2C is just conjugation by a special linear matrix. And then we can just play with those special linear matrices and reduce, and then we end up with 3 classes of non-isomorphic classes of the algebras. So there is a class which involves, well, actually all generators, E, F, and H. Okay, so it's essentially all that I wanted to say about those Lie algebras. There is something I wanted to add to this idea given by Paulo Saraco yesterday. So I would like to advertise a conference, okay, just to finish. So the next year, there will be a one-week conference in Bendlewo in Poland, the Banach Center workshop on the Young-Baxter equation and all that. So if I am successful, I can... Okay. Should I say? Okay. Okay, you can get more information on the web page. It already exists. There is a gallery of speakers. Some of them, at least, were present here. I don't know if Giovanna is still in the audience. Okay, so you are all welcome to register. The registration page is not yet operational, but it will be operational soon. You can get more information from the web page. So thank you very much.
So, are there any questions or comments?
Thank you for the talk. Just a comment. I'm pretty sure that for a fixed field, Lie algebras form a Maltsev variety. So there's a general theory of that, and there are very nice features. For example, congruencies behave very well in Maltsev varieties. So maybe this can be of help in some sense.
Mm-hmm. Yeah. Thank you.
Okay.
Can we kill this side?
So when you had the condition with lambda and delta, so you were starting from the algebra and...
This one, right?
Yes.
Mm-hmm.
When you, on the previous slide, so my question is here, the condition is not symmetric on lambda and delta, this condition star. You have lambda, right, playing a different role from delta.
Yes.
But on the previous slide, in the definition of the bracket of the
algebra.
Yeah, algebra.
It's not symmetric either. So there are.
Oh, can you show it? 'Cause
yeah. So there are two versions. And so you can place the brackets either this way or the other way, where the bracket, the nesting is on the first arguments, and write the Jacobi identity. So it's not symmetric in the sense that we write A bracket BC, not bracket AB and comma C.
Okay.
So that's why there is a lack of symmetry with this respect. But it's like a left and right module, so you can always translate from one to the other.
Okay, okay.
And so that's why there is the role of lambda and delta is not symmetric, as you noticed. Yeah.
Thank you.
Okay.
So 2 questions. Can you write down a version of restricted Lie algebras in this language?
Can you repeat?
Restricted Lie algebras can be also written down in this
The restricted
setting.
Can you say it again, please?
So a restricted Lie algebra is a Lie algebra with a P operation in characteristic P.
We haven't thought about it. I mean, the problem with restricted, or if you start talking about some nilpotency properties and so on, when you cut off at some point you say, well, what does it mean cutting off? You set something to 0, and that's a non-trivial thing in this setup. So we haven't thought about it, no. But it's a nice question, thank you.
And there are other structures beyond the Lie algebras that you can...
Yes, so the first structure that appeared in this setup was what we called, and I excuse my British colleagues, truss. That was before our Prime Minister, the shortest in the history. So it's an idea of the generalization of a ring. So it's a distributivity. So as we seen from Marcelo's talk, you can't have a nice distributivity on both sides if you have binary operations. Because then you end up with the argument, which tells you that, well, you end up with an abelian. They have to coincide, and you have the abelian thing. But as you know, there are braces where you have additive, well, you have two groups distributing, one distributing over the other, but in some non-trivial way. And this is a special case of the distributivity over a ternary operation, over a heap. And the distributivity, if you think about it, well, it's equivalent to say that you have a bi-affine property or bilinearity, bi-additivity of your multiplication. So you can do associative heap with an associative operation on it and distributing over the heap operation. And this is also related to joins braces with rings on one hand, and on the other, you can fully. Again, this is a good affinization in the sense that when you specify, you have your linearization of the multiplication will give a unique algebra structure, and you can all fit, and then there is a way back through the extensions. So you extend integers by, or you extend. You extend integers by rings, non-unital extensions.
Okay, there's the last question by Marcel.
Thank you. I have just a question. Can you define something like pre-Lie algebra or associative algebra that corresponds to this Lie algebra?
Yeah. So you can define the pre-Lie algebra, and so this is a part of the, it's a sort of pre-associative stuff. So you start, well, axioms look very much the same. So this is in the period, in our paper with James Papworth, we have a pre-Lie algebra, and then the specific, excuse me, it's not exactly a commutator because the commutator doesn't make sense. You need to have odd number of terms in your expression for the, so the commutator plus a correction gives you the Lie algebra bracket, yeah. So.
Okay, that's time speaking again.
Okay, thank you.
We have a break of 0 seconds.
Minus 5 minutes. Negative.
And he will talk about Hopf algebra structures, Hopf algebras, and monoidal calculus.
Yeah. Okay. So now I think first I would like to thank the organizers and Claudia and to invite me to give a talk at this nice conference. So I enjoy a lot other people's talks. So I will talk about this area called Hopf algebra structures, and I will give some historical, so to say, it's historical semi-historical points and of how it appeared first, and then also some results during those times and later, and I'll make some connection to coalgebras, bialgebras, and maybe if there is time at the end, we'll mention something about Hopf algebras or categories, but that depends on the situation with time. First I wish to mention that this area of Hopf algebra structures was introduced by me and at that time 2 of my former master students, and then one of them became my PhD student and defended PhD, actually first PhD student having this in his dissertation, Daniel Larsen, and Jonas Hartwig, he was my master student at that time, but then he moved on due to money reasons to another person in Sweden and defended his PhD in representation theory of highest weight modules and so on in another city not related to home algebra. So, but he is now in the United States, and both of them are, I think, professors in the universities in Norway now, Daniel Larsen and Jonas Hartwig in Iowa, in Des Moines in the United States. Yes, so the area started in about 2003, and I wish to mention that it was a year of non-commutative geometry in Mittag-Leffler Institute, and then it was also a little bit after this, and also related to this, it was a European network Ligritz, which was very important for my life because scientific life, it was very useful, and the person there was quite nice person, Fred van Oysten, who invited me to these things, and also so it was quite nice, very nice activities and very nice things happening, and then after developing this area have exploded, so there are many people in different countries and continents working on this. So there are people in China, India, in Africa, in several places, in Europe, and in Latin America, there are very nice groups of people working with home algebra structures. The area developed so much that in 2020 it was decided by American Mathematical Society to include two of the classification items related to home algebras. And this was, I have no contacts with American Mathematical Society, so it happened beyond any kind of pushing from my side. I have never contacted anybody in American Mathematical Society myself. So that's the first thing. The second thing is that where come motivation for these structures? From my side, it was from papers from 90s by Kulish, Prishnaider, Lukersky, several other people, Isaev, and several other people, about Q deformations of Witt and Virasoro algebras, and in conformal field theory and quantum field theory. And in that, and I will mention more a little bit about them, but also from various oscillate algebras, or Q-deformed oscillate algebras, and examples there, from Q-deformations of differential and homological algebra. Also about the same time in 90s appeared Q-deformations of papers on Q-deformations of homological algebra. And also another side, it's colored Lie algebras and superalgebras. So it's another development. So colored algebras, superalgebras, and more general colored algebras. It's another motivation for this subject. I will explain how they come together. And then there are various examples from various kinds of non-associative algebras and from non-commutative geometry, which motivated me at that time. So if we start with the sigma derivations, this is a linear map on an algebra, let's say commutative algebra. where Leibniz rule is twisted by a map sigma, and sigma it can be automorphism, but it can be also endomorphism, these are called sigma derivations. It's an old subject which goes back to more than 100 years at least. Now, in this paper in 2003, which was published as a preprint in Metagraph Institute and also as a preprint in my university at that time, where I worked in Lund University at that time. And then after almost more than 3 or 4 years, it appeared in Journal of Algebra. Then we proved the following theorem, that if you have such sigma derivation, or sigma, then we can take the sigma twisted vector fields, so with the coefficients in this algebra on which sigma derivation acts. And then I was looking for this for some Lie type structure which would sort of extend those Q deformations of Witt, Virasoro appearing in those papers, because at those papers they discovered by trial and error, simply by hand parameter calculation, Q deformations of Jacobi identity. Okay, so in some of these papers they really wrote up in some appendix or in some calculation, they said, and okay, so this Q deformation of interesting Q deformation of Jacobi identity is satisfied for those Q deformed algebras there. Basically, all of these examples are based on so-called usual Q derivatives. So discretizing derivative by from mathematical point of view, it's discretizing derivative by Q derivation, Jackson Q derivation since 150 years or 100 years. No. So and then when you do this discretization, Leibniz rule is deformed, and since Leibniz rule is modified, the Jacobi identity calculation for Lie algebras is not true, so Lie algebras are not there. So you need to, and you're looking for modification of a Lie structure. Okay, so because if you modify Leibniz rule, which happens in almost all discretizations of derivatives, then commutator is not a Lie algebra anymore. You calculate, you get second order terms which don't cancel. So we were looking at this, and then we found this bracket. It is twisted by this map sigma from the Leibniz rule in this way. So this is Q-symmetric bracket. And if you calculate it using twisted Leibniz rule, you get on the right-hand side again a vector field. Okay? This discretized or vector field. And we discovered that if sigma derivation and sigma satisfy intertwining relation, like Q commutation, like in quantum plane, but here you can put any element from the algebra, actually, it's more general. If this extra condition is satisfied, then we get such 6-term Jacobi identity, which is twisted by map inside here. It is this sigma, and then delta is multiplication by an element from this element from the algebra, and we get this 6-term Jacobi identity. All those Q deformed Jacobi identities appearing in those papers, they are a very special case of this, of course, because Q derivative is a very special, one of the first examples of sigma derivation beyond usual derivative. Yeah? And if A is a unique factorization domain, you can compute it simply as a quotient of sigma of G divided by G, where G is greatest common divisor of the image of your algebra A by identity minus sigma by difference operator like this. So you can compute it very easily here. You don't need by trial and error fit the coefficients in the complicated calculations. You just plug in and you get your Jacobi identity and 6-term twisted Jacobi identity in this way. We introduce then, but then it is Q-symmetric, so it doesn't include superalgebras and colored Lie algebras, and this is another motivation. So we need to, and I wish to have this within the same structure, so that when you move parameters to limiting values, you recover either Lie or super or colored cases in most situations. So we have this in 2005. We have with Larsen, we have introduced this very general structure, and actually colored version of this structure, where you have a space graded by abelian group. You have this twisting mappings defined on the homogeneous elements. So they are partially defined, not on the whole algebra, but on homogeneous elements. You have skew symmetry twisted by an operator here. So it's not just a constant or scalar, but it is an operator acting on this side, on this bracket, depending on this x and y. And this and 6-term Jacobi identity twisted by actually not 2 but 3 maps also. There is this outside twisting the whole thing, which is an operator. Okay. This structure includes also colored case, and there are some important substructures as non-graded case. So you just if group is just one element, Hopf superalgebras, quasi-Hopf superalgebras, quasi-Hopf colored algebras, everything in 2005 in our paper, it's included here in this structure. And then so-called quasi-Hopf algebras with an extra identity saying that alpha is a homomorphism up to twist by beta. So it is a kind of more general multiplicativity of alpha. Yeah? Colored Hopf algebras are, of course, special case, and here you have commutation factor from colored algebras, so by character participating, it's a special case. Here, the identity is cyclic summation, and then it's twisted by one map alpha, and then you have this on homogeneous elements. You have this situation. Of course, Hopf superalgebras, it's just the Z2 graded case. Okay. You have, then we have here, if you don't take grading, you just take non-graded, so group is consisting of one element. Then we get, this is what is called what is now called Hopf algebras, okay? This become a first object of study, and many papers appeared about Hopf algebras, Hopf modules, and many other constructions, classifications. Now, about Hopf algebras, because it's only one twisting map, twisting the Jacobi identity, and skew symmetry is still like this. So this structure actually, in the case of those constructions with sigma derivations, we get also such as in special cases, where the 6 terms collapse to 3 terms, and when you need only one map to twist. Okay. So, for example, for Q derivative, you'll see later. And those examples in papers, Kulish, Schneider, Lukerski, and so on, there is no 6 terms identities. There are this 3 terms, Q-deformed identities. So there is a trick which works actually for all kind of Hopf structures in basically a similar way. How you can, so if you have your favorite Lie algebra, or maybe associative algebra, or maybe some other algebra structure, and you take an endomorphism of this full endomorphism, not just a linear map in this case, but endomorphism of this structure. So if you take a homomorphism of this, for example, simplest case of this Hopf algebra into itself, and you take your of Lie algebra into itself, and then you compose your multiplication in Lie algebra with this alpha. You get a new multiplication here, but that is not Lie algebra anymore. But it is exactly Hopf algebra. Okay? So you will get skew symmetry still, but the Jacobi identity will exactly have this alpha in this place. It's a special class of, in this way, from Lie algebras to Hopf algebras, by this push forward, I call it push forward trick, because it is really a push forward of the structure, okay, by alpha. So you don't get all Hopf algebras. So there are Hopf algebras which you cannot get from Lie algebras. Okay, so many of them. But this is at least a way. If you have your favorite structure without an extra unary operation, then you can get this Hopf algebras by, for example, this composition, such composition. But not all Hopf algebras or Hopf structures are obtained from usual structures in such a way. That's another point I wish to point out. So this is one of the examples which you can find with some parameters changes in this paper, this 90 papers from 90s which I mentioned. This is connected to Q derivative. So you have this Jackson Q derivative from almost 150 years ago, or maybe more. Then It is a sigma derivation with a rescaling by Q. So Leibniz rule is deformed by such sigma. It is if Q is non-zero, it's automorphism of the algebra of Laurent polynomials or of polynomials. If you compute that bracket in that theorem which we proved, then you get on the left-hand side such Q deformations of a commutator with Q in power n participating depending on the generators. And generators, I should mention, are those standard generators given by minus t in power n delta, but now derivative is replaced simply by discretization. So what we are doing actually, we are replacing derivatives systematically by sigma derivations. That is what we are doing and looking for what structure. This is structure, okay? So on the right-hand side, that bracket gave a K vector field, and it becomes this. So it is graded, it's n plus m here, and it is a difference of Q numbers. Q numbers, as you know, it's just sum of geometric progression up to n minus 1 and m minus 1 with quotient Q, okay? So Hopf-Jacobi identity become like this, and the alpha is a diagonal operator acting on these generators with this eigenvalues Q in power n plus 1, okay? So Hopf-Jacobi identity is looking like this, okay, in this case. And when Q goes to 1, of course, we recover Witt algebra of vector fields on the unit circle. We looked at the central extensions in the follow-up paper with Larsen in Journal of Algebra. This paper, this second paper, it appeared actually before the first one. It looks like this, but it is not like this because the first one gets stuck for almost 3.5 years waiting for something. But since then, we published several more papers which appeared slightly before. So it's this is why I always point out preprint versions as original and not the journals versions, which is always delayed. So this is Virasoro. So when we computed central extensions in a very solid way with cocycles and so on, but for Hom algebras, for quasi-Homely algebras, which means that we are requiring that structure in the such extensions. And then we obtain, for example, for this example, this Q deformation of Witt and Virasoro. That deformation. When Q goes to 1, you recover here 1 over 12, that famous string theory way of writing this cocycle, central charge, it's called. And then the bracket is the Hom bracket, so that bracket. And well, loop algebra construction also functions well. I will be now jumping through the slides. If you take endomorphism of a Laurent polynomial, so you take nonlinear transformation f of s, x t goes to f of t in power some s, and you compute that bracket, you will get on the left-hand side mixture of 4 types of generators scaled here by s, and then here q in power n, q in power m. So it's a kind of commutator of 2. A bracket of 2 will become expression, quadratic expression in these 4 generators with this multiplicative shift of the index coming from that sigma derivation. And then when you compute the bracket, you will get this on the right-hand side. So it's a linear combination of these generators. It's impossible to compute by hand. It's difficult to compute Hom-Jacobi or what Jacobi identity will be satisfied when you have this in this way. But with our theorem, we just can plug in, and since we on unique factorization domain, we just compute that delta. And then sigma we already know, and this is identity satisfied. So we don't need to do any more computations, actually. We get it, okay? It's quasi-Homely algebra. So if you choose another way of defining this, you will get a more simple brackets here. So if you take, in that case, we took this quotient, difference quotient, because it's difference between t and the action of the sigma and this identity minus sigma. So this is our replacement of derivative in this case. But so it's a divided difference, and then. But here, if you divide just by t in power k, so by the variable t in power k, then and do this, then we will get this more simple bracket, but here the indices will be shifted also in a little bit more complicated way and rescaled here. But you have this more simple right-hand side, and you get such Jacobi identity, sigma deformed Jacobi identity. Interesting is that this is almost graded, so it's not graded anymore in all these cases, but in this case, it is, we call it hyper-almost graded algebras, where the summation on the right-hand side of the graded axiom is along certain span of the direct summands, okay? And this span is very clearly controlled exactly by the endomorphism power, so the sigma t in power s, so this s comes in here, and shifting here by that k which you divide here. So the span is given, it's growing linear in that power of s, and so it's a more general, and such actually algebras also appear in something called Krichy-Vernoyek and top algebras in another way. So, okay. We asked with Nasser Maklov sitting there in 2006 about something called home associative. What is replacement of associative algebra? So this is a question which we asked, because if you have associative algebras are Lie admissible. Okay, so this means that if you take a usual commutator, you get a Lie algebra. That is sort of first calculation you do in any course on Lie algebras, but that is a very fundamental property. Okay, so it's called it's called Lie admissibility. Okay. Of associative algebras. But now we have home Lie. So if you have home Lie algebras with one map twisting, a Jacobi identity, what is then we should do? We tried the various Q deformations of the bracket and some putting this and that doesn't work. So we made, we asked what will be replacement, natural replacement of associativity structure, how we can replace associativity structure in different ways so that commutator leads to a home Lie. So we went another way without sigma derivations, now more abstract structure, okay? And we found this home associativity condition, so this alpha is from home Jacobi. If this condition is satisfied, which you can be easier read like this, where alpha twists the first term and the last term in the associativity, okay? So it's not associative structure in general. Yes, but if alpha is identity map, you get associativity. Otherwise, it's in most cases, it's not associative. It's family of non-associative algebras parameterized in this way, special way by linear map alpha. So alpha is just a linear map now. Just a linear map. Okay. Turns out that if you have this home associative algebra, then the usual commutator become home Lie. Okay. So that theorem we proved in 2006 when I met Nasser in a conference actually organized again by Fred Van Oysten in Belgium. I think Steph was also kind of involved in the organization. Yeah, it was in Spa. It was a wonderful conference, and thank you very much. Send my best regards to Fred as well. Yeah, so then we start looking at this, and then we found this in that paper published in 2008, but then in journal, and then 2006 as preprint. Then more generally, if you have a subgroup of a group of three elements, one can define so-called G-home associative algebras using alpha twisted associators in this way. So this is, and then turns out that they are also home Lie admissible. So the commutator will lead to home Lie algebras. Now I just wish to mention that in that paper, thus for different subgroups of S3, we get home left symmetric algebras, so generalization of left symmetric or Weinberg algebras. We have home pre-Lie algebras, everything in that paper. They introduced by us at that paper in 2005, 2006 with Nasser. As an example of home Lie admissible constructions. Okay, and there are some other interesting algebras with 6 terms such identity but twisted by alpha. Okay, but the name of this, I'm a little bit looking for this, what happens with alpha going to being identity, and what is the name for that in the classical without any extra operation. Okay, now just very briefly I will mention, I have still, I think, so 6 minutes, and then if you have, then we wrote 2 papers with Nasser McGrath about Hopf algebras and Hopf algebras. It was published in 2008 first, and then in a journal in 2010, and then another paper was published in a Springer volume for conference, which was organized actually by me in Lund, but it was in 2009, follow-up paper to the first one. And there we have looked at the co-algebras, co-algebras, Hopf bialgebras, and Hopf algebras. So there we and also Hopf-Lie admissible co-algebras and so on. So this first time appeared in those papers. So then this area actually developed very much. There are many papers now extending and studying this Hopf and various constructions connecting to Hopf bialgebras and extending them and so on. I think Nasser will talk about one of such extensions in his talk. If I saw the abstract, so I sort of guess about this. But here, Hopf algebra, I have just little time, but Hopf bialgebra is defined in this way, where you have this beta, it's an extra operation here, and so you have this co-product, and then you have an extra operation. But then Hopf co-associative algebra has this this Hopf associativity condition. So if you reverse the errors in the associativity, so you will get this condition, depending now on the linear map for beta. Okay. And if beta is algebra endomorphism, so it satisfies multiplicativity, this becomes so-called multiplicative. Sometimes called monoidal, sometimes called Hopf co-associative co-algebras. Okay, you can cook up monoidal categories. So now I said what category, no more time to say more. But you can from those. But if you have just a linear map, then you are beyond. So you can construct things which are not monoidal categories, of course, but it's still manageable. So you can prove things up to some level. So then you need to do some modifications. And now push forward works as usual, and then we have this. Well, I just directly jump to this, that G-Hopf coalgebras are Hopf coalgebras which satisfy the co-version of that G-Hopf associativity. So G-Hopf co-associativity. And one can show that any G-Hopf algebra is a Hopf-Lie admissible Hopf algebra. And the definition of Lie-Hopf admissible Hopf algebra can be written in such way, using such difference, and then the condition can be obtained in a very explicit way using Hopf co-associators. Okay? I will not go into more details here. And there are thus analogs of Hopf Weinberg or Hopf left symmetric and Hopf Prelie and so on, but in core version. So there is duality situation, and here I just wish to mention that so the dual space of a Hopf co-associative coalgebra is a Hopf associative algebra where maps are transposed on a dual space. And then if you have finite dimensional k-vector space, and you have, well, one can define Hopf algebra if you add, so with some modification definitions of unit and co-unit, you can we defined Hopf algebra, and then there is the dual ones will be Hopf. So if you start with Hopf, so for Hopf you recover the same thing, but for co-algebras and algebras you have Hopf algebras, Hopf algebras. In one of the directions you have finite dimensionality, which sort of gets in. And so this is last slide. I don't have time for this, but I wish to mention also a paper which was actually quite also heavy history, but usually papers which get stuck, finally they get attention. So this is why I wish to bring it to your attention. Huh? So this is a paper which was actually written already around 2017 and reported to the conference. And then we finally, in 2020, after a lot of delays, it was published in a Springer volume, so you can access it from your university, or I can send it to you. And since there are many people sort of interested in Jette Driefield and category and some other stuff, I will just show here just an abstract for this paper, because there is no time to, it's more complicated constructions. So in that paper, one can define Hopf Jette Driefield category via Radford by product. And then if you have a quasi-triangular Hopf algebra, then we prove that the corresponding category of H beta Hopf modules is a braided tensor subcategory of that one. And as a generalization of Radford by product Hopf algebra, we derive necessary and sufficient conditions for R smash product Hopf algebra and T smash product Hopf algebra to be a Hopf algebra. And we give some non-trivial examples in that paper. In the end of my slide, I have these references, plus also I added this paper with Tianshui Ma and Cheng, which is called On Hopf Jette Driefield category, and I would be happy to have some, to give another talk, but that is beyond the scope of the time we are given here. Okay, thank you very much.
Are there some questions or comments? So on one of your slides, there was a generalization of grading, where the grading was not multiplicative.
Where?
I don't remember which slide, but there was a generalized type of grading.
Oh, with a billion group?
Yeah.
This is with a colored version. So where you start with a billion group, and when you start, skew symmetry is twisted.
Yes.
by
Yeah, but there was a slide where you had something, if you have something of degree alpha, say, and something of degree beta, the degree of the product is not alpha beta, but it is...
This, which we call hyper quasi... So this is for this example. So we have the span of the grading.
Yeah. So I was wondering about the following. We all know that a graded algebra is, in the language of Hopf algebras, a KG co-module algebra. Is this type of grading, is this some type of Hopf co-module algebra? Or has that been investigated?
This, I think, well, this is, we get it in the examples, so to say. So in the example, we get this type of generalization of a graded algebra. And in this example, associated to endomorphism stuck into twisted Leibniz rule, we get this structure with this span. Of course, abstractly, it is if you look at this, it's a generalization of a graded case. And now, whether you can, from any such graded, go back and recover underlying Hopf structure, which would lead to that I am not completely sure. But maybe through some twisting constructions or some twisters. I don't know. But it is a very good question actually to investigate. We have examples. But we don't have a general construction in this way, which would sort of cover them. Yeah. Okay.
Okay. Any other questions or remarks? If not, let's thank the speaker again. And there is a coffee break.
Okay. Thank you very much.
Okay, let's start. So our next speaker is Juan Cuadra from Almeria, and he will talk about constructing integral Hopf orders in twists of certain group algebras. Please.
Okay, thanks, Steph. I would like to start by thanking the organizers for organizing this nice conference and for giving me the opportunity to speak here. So in this talk, I will speak about this preprint in collaboration with Ehud Meyer from the University of Aberdeen in Scotland. And in this work, we keep going on with our study of integral Hopf orders in semi-simple Hopf algebras, but changing in our previous line of action. So, as many of you know, our previous work on integral Hopf orders was focused on the phenomenon on the non-existence of integral Hopf orders in semi-simple Hopf algebras, which are constructed as twist of Drinfeld-Mosev twist of group algebras. And in this paper, we focus on the existence instead of the non-existence, how to construct integral Hopf orders and their uniqueness. So this is more or less the summary of my talk. And say that my goal will be to present a group theoretical condition under which a twist of a group algebra admits an integral Hopf order. So in the first slides, I will try to give a global view on this topic, and afterwards I will focus on the new results. So for this global view, let's start with a few introductory words on the general theory of orders. So the theory of orders lies at the intersection between algebra and number theory. So in the preface of Reiner's foundational book, Maximal Orders, we find the following sentence: the beauty of the subject stems from the fascinating interplay between the arithmetical properties of orders and the algebraic properties of the algebras containing them. And this interaction is particularly strong in the representation theory of finite groups. So for a finite group G, the group ring set G inside the complex group algebra CG is one of the most significant examples of orders. So an important result here, depending on the existence of such an order, is Frobenius' theorem, which states that the degree of any complex irreducible representation of D divides the order, and perhaps more appropriate in this setting, the size of D. So if we view the complex group algebra CG with its customary Hopf algebra structure, then it turns out that the group ring set G is a Hopf order of CD over Z. This means that we consider the group algebra CG as a set module by restriction of scalars, then ZG is a submodule of CD over Z, which is finitely generated and projective as a set module. We can get CG by extension of scalars from ZG, and ZG is closed under all the Hopf algebra operations, okay? So here, if we replace the complex field number C by any arbitrary field, and we take a subring of that field, we can define in a similar way the notion of Hopf order for any finite dimensional Hopf algebra over a ground field. Good. So for semi-simple co-commutative Hopf algebras, that is group algebras, a rich theory of Hopf orders emerged from these two seminal papers by Richard Larson. There are two books, one by Childs and another one by Underwood, in which this theory is very well expounded. But on the other hand, the theory of quantum groups emphasizes Hopf algebras that are neither commutative nor co-commutative. And in contrast, little is known in this setting about Hopf orders. So our initial interest on Hopf orders was mainly motivated by Kaplansky's sixth conjecture, which is still open, and it is a generalization of Frobenius' theorem for semi-simple Hopf algebras. So this conjecture states that in a complex semi-simple Hopf algebra H, the dimension of every irreducible representation of H divides dimension of H. Okay? So when I was a postdoc in Antwerp, long time, 20 years ago, 25 years ago, I learned that Hopf orders were considered as a way to solve this conjecture because the following result by Larsson, which states that the conjecture holds if the Hopf algebra admits a Hopf order over a number ring. And this is what we call an integral Hopf order. And as I told you, at the end of last century, this was the question that was on the air. So as a consequence of the finiteness result for the isoclasses of semi-simple Hopf algebras over the complex number field, it can be proved that every complex semi-simple Hopf algebra can be defined over a number field. Okay? And the question that was on the air at that time was the following. Assume that H is a semi-simple Hopf algebra over a number field K, which splits as an algebra. This means that H is a direct product of matrix algebras over K. That H admits a Hopf order over the ring of integers of K. So an affirmative answer will solve the conjecture, and I could tell you some of the opinions that were at that time on this question. But several years ago, we provide a negative answer in these two papers with Ehud Meyer. And the families of examples for which this phenomenon occurs are twist of group algebras in Drinfeld-Mostev way. So the twist modifies the co-algebra structure. So our way of using the twist will be at the co-algebra site, not at the algebra site as in other talks in this meeting. And the twist modifies the co-algebra structure and the antipode, but leaves unchanged the algebra structure. So as algebras, they are group algebras, so they satisfy the conjecture. Okay, so indeed, we are not touching the Kaplansky's sixth conjecture. What our results say is that to prove Kaplansky's sixth conjecture, the original proof of Frobenius' theorem does not degeneralize, at least in a direct way, to semi-simple Hopf algebras. Okay. So what we are saying is that there is not a direct proof, as in there will be not a direct proof as in the group case, and if Kaplansky's sixth conjecture is true, something else should be needed to prove it. And another interesting thing of the families that we analyze is that these are simple Hopf algebras, so their only normal Hopf subalgebras are the trivial ones. And indeed, we wondered whether the simplicity is the reason for the non-existence of Hopf orders. So more precisely, in our second paper with Udi Meyer, we proposed the following question. So let H be a simple and semi-simple complex Hopf algebra, which is non-trivial. So non-trivial means that it is not a group algebra, nor the dual of a group algebra. And we ask, can H admit an integral Hopf order? Okay. So in this generality, we think that this question is difficult to answer, but the following particularization seems to be more approachable. So let G be a finite non-abelian simple group, and G a non-trivial twist for the complex group algebra, which arises from a 2 cocycle on an abelian subgroup. I will make this more clear in a few minutes for the non-expert. So we consider the twisted group algebra. Can't it admit an integral Hopf orders? That means a Hopf order over a ring of integers of some number field. So we gave a partial negative answer in this paper in collaboration with Giovanna Carnovale and Elisabetta Massoud, which was published recently. And surprisingly, we reached a result that it was not, when we formulate the question, it was not, we thought that proving something like that was out of reach. But we were able to answer negatively this question for several families of finite non-abelian simple group. So we have a complete answer for the projective special linear group of size 2 over a finite field. And we also have a complete answer for the Suzuki groups. And as a consequence of analyzing these several families of non-abelian simple groups, and using the classification theorem of finite simple groups, we can prove that for any non-abelian simple group, finite non-abelian simple group G, there exists a twist J such that the twisted group algebra does not admit a Hopf order over any number ring. That is our partial answer. Okay, so far I tried to provide a global view on this line of research. So as I told you, our previous work was focused on the phenomenon of the non-existence of integral Hopf orders, but now we will change our perspective and we will focus on the following question. So assume that G is a finite group and G is a non-trivial twist for the complex group algebra. And suppose now that this twist is not simple. What can we say about the existence of integral Hopf orders in this case? So we knew a bit about this question in our second paper. So in the analysis of one of the families, there was an exception that we have to deal with. And indeed, in that exception, we found that integral Hopf orders do exist. And it was the following. So K is now a number field, and we consider the group, the symmetric group on 4 letters. So we found that there is a twist for the group algebra on the symmetric group of 4 letters and coefficients in K, such that the twisted group algebra admits a unique Hopf order over the ring of integers of K. So that was the only example that we knew at that time. And the goal of this new preprint is to fit this example in a general group theoretical framework. And this is something that we achieve. And now we understand this example much better. And that will be the main goal of this talk, to present this general setting. Okay, so we now begin with the technical part of the talk. I have 2 slides about Drinfeld-Mosseff's deformation procedure. I don't know to what extent I should enter or not too much, because this is there is many specialists in the audience. But let me at least just to fix notation to go a bit quick on this. So we say that an invertible element J in H tensor H. Now H is a finite dimensional Hopf algebra over some ground field K. So an invertible element J in H tensor H is a twist for H, provided that these 2 conditions are satisfied. Okay. So the first one is the dual notion, the dual version of generalization of the 2 cocycle, of the condition of 2 cocycle on a group, and the second one would be a dual version of the notion of dual version of generalization of the notion of normalized two-cocycle on a group. Okay, just to, if we given such a twist J, we can construct another Hopf algebra, Hj from H, in the following way. So Hj equals H as an algebra. The counit of Hj is that of H, and there is a new coproduct and antipode where J plays the role. So the co-multiplications of this new Hopf algebra is defined from the co-multiplication of H conjugating by the twist, and this needs to modify the antipode as well. So the new antipode is conjugating the old antipode by this invertible element Uj that is defined here. Okay, so at least I need to present these formulas and bear them in mind because they will play a role later in the proof of our main result. Okay, so this is the general concept, and now we see Moseff's method of constructing twist for group algebras. So G is a finite group, and we consider the group algebra Kg, and we are going to take M an abelian subgroup of G, and M hat its group of characters. So for this to work well, we need that K is large enough so that the group algebra Km is splits, that is decomposes at the direct sum of copies of K, so many copies of the size of M. And it turns out that the Bederboot decomposition of this group algebra Km can be completely described. So the primitive idempotents are parameterized by characters phi of M, and the corresponding primitive idempotent for a character phi is given in this formula. Okay, it's given by this formula. And I would like to ask you to watch to this fraction 1 over order of M, because it is going to play a role. So now, if we have a normalized two-cocycle on the character group of M, then this formula defines a twist for Km. So twisting Km is not does not produce anything new because Km is commutative, but since Km is a Hopf subalgebra of Kg, this is still a twist in Kg, and if G is non-abelian, then it can produce something new. Okay, and watch now that when we perform the twisting procedure on the group algebra via this twist, we are introducing among the structure constants of this Hopf algebra, we are introducing the fraction 1 over size of M squared. Okay, so this means that in principle that could be thought as an obstruction for this Hopf algebra to be defined over a number ring. And that was our naive original idea when we found this example. And surprisingly, it happened that sometimes it is an obstruction and sometimes it is not. Okay? So in the series of previous papers, it turns out that it is an obstruction, and as I will show you later in the new result, it is not. And the only difference between these examples is that the ones for which this is an obstruction turns out to be simple Hopf algebras. So we think that really the simplicity is playing a role here, but we do not see the reason we do not understand the reason or how the simplicity is playing that role. Good, so I'm done with the twisting technique. So now we have to go further and to formulate our main result and to give you an idea of the proof, we have to work in a more detailed way with the twist. And for that, we need the concept of Lagrangian decomposition. So suppose now that B is a non-degenerate skew-symmetric pairing on the group M with itself. And for a subgroup L of M, we are going to consider the orthogonal complement L perp. Then we call this subgroup L a Lagrangian of M if L equals L perp. Okay? Good. So then, through the bilinear, the non-degenerated schizometric pairing, we can define a map, a group homomorphism pi from M to L hat, whose kernel will be L perp, but if L is a Lagrangian subgroup, and then L perp equals L, and we are going to have this short exact sequence. So suppose that this mass pi splits, and then M would be isomorphic to the direct product of L with its character group L hat. And this decomposition is called a Lagrangian decomposition of M. So Lagrangian decomposition were studied by Davidot in this paper, which appeared in the proceedings of another Hopf algebra meeting, this one in Brussels, 14 years ago. And he proved that a Lagrangian decomposition of M always exists, and writing every element of M as a pairs G lambda, where G is in L and lambda in L hat, we can, B can be read in this form. So B arises, say, roughly from evaluation from L hat on L. Okay. Yes, yes, and this is going to happen if you have a non-degenerate skew-symmetric a non-degenerate skew-symmetric pairing, because this is going to be a group of central type. Yeah, exactly. So M is a bit special for this. It should be a group of central type. Okay. Good. Okay, so I will tell you now how to apply this to a Tuco cycle. So I will tell you how to apply this to a Tuco cycle. So we take, given a Tuco cycle on M, we can construct a pairing B alpha, Tuco cycle alpha, a pairing B alpha, in this way. And we call the cocycle non-degenerate if this bilinear form is non-degenerate. And it turns out that using this Lagrangian decomposition, this cocycle alpha can be expressed in this form. So where now it comes from evaluation of L hat on M. So if we have an element in M, a pair in M of the form G lambda, and an element G prime L prime, then the cocycle up to co-boundaries will be given by evaluation of the second component of the first pair on the first component of the second pair. Okay, so that's a very good way to write the Tuco cycle. Okay, and now I'm ready I have all the ingredients in my hands to formulate the result. So we have K a large enough number field. We need K to be large enough because in the previous result, when we say up to co-boundaries and the proof of those results, we need to enlarge K to achieve that. So the good thing is that we don't we don't need to go to the algebraic closure, but we can do finite steps to achieve that. So we do not lose that K is a number field. So G is a finite group and M is an abelian subgroup of G. And now we take omega, a non-degenerate Tuco cycle on the character group. And we consider the twist afforded by omega. Okay. And we are going to fix a Lagrangian decomposition of M hat. Okay. Previously I applied all the Lagrangian tool to M, but indeed we are going to apply it to M hat. So we can apply the Lagrangian decomposition to M hat and make sure that omega up to co-boundaries is given as before. And now here the condition comes. If L, we view L as inside of M, And if this is contained in a normal abelian subgroup N of G, then the twisted group algebra admits a Hopf order over the ring of integers of K. Okay? So see here that, again, we are approaching the original question, but from another point of view. So we are going to suppose that our group G is not simple. So it will contain a normal subgroup. And what we are asking is that it is abelian and that it contains the Lagrangian. So somehow, indeed, we are working with the original question, but from another perspective. And in this case, we are able to say that there are integral Hopf orders in this case. Okay? So see that a very easy way of fulfilling this condition is that M itself is contained in a normal abelian subgroup of G. So the abelian subgroup giving rise to the twisting is contained in a normal abelian subgroup, then the twisted group algebra will admit an integral Hopf order. So what we are doing here is to refining that condition. So, and we have examples where M itself is not contained in any normal abelian subgroup, but there is a Lagrangian decomposition such that L is contained. So it is a real refinement of that. Good. Then I will tell you in the last minutes about the proof. So the idea of the proof is to construct a Hopf order of the group algebra such that the twist and its inverse belongs to the Hopf order tensor with itself. And then what is going to happen is that this Hopf order will be closed under the coproduct and the antipode, or in other words, we are able to perform the twisting at the Hopf order level. Okay, that is the idea. And so I will give you a sketch of the proof. So the first part is to write the twist. So the first part is to write the twist well in a suitable way to achieve that J and J inverse is in this Hopf order of the usual group algebra. And this we can achieve using Lagrangian decompositions. So if we fix a Lagrangian decomposition of M hat such that the omega is given as before, then we can write the characters of M in this way as pairs G lambda with G in L and lambda in L hat. And we can make sure that this works well with duality so that M itself, we can also consider, the elements of L can be also considered as pairs lambda prime G prime with lambda prime in L hat and G prime in L, okay? So that indeed the evaluation of M hat at M will be given or will become just from evaluation from L hat on L, okay? That would be the idea. And then, once we have written the characters of M as pairs in this form, the primitive idempotence in Km will be, can be written, so for a character G lambda, the primitive idempotent EG lambda will be rewritten as the product of E lambda EG, where E lambda is in KL and AG is in KL hat. Okay, that is the idea. And the good thing for us is that the twist in Km, once we have the cocycle expressed in that way, it turns out that the twist J in Km is related to dual basis. So we can express J in this way. So J is the sum of E lambda tensor lambda, where lambda runs in L hat, or alternatively, we can write G as the sum of G tensor EG, where G runs in L. And the same is going to happen for the inverse. So as a result, J belongs to KL tensor KL hat. So we make sure that J has this property, okay? And now what we did is that we are going to take a Hopf order constructed from this primitive idempotence. So X will be the OK subalgebra of KG generated by elements of this form, A nu times G, where nu is in N hat, and G in G. And since N is normal, G acts on N hat by this formula. And this is telling us that conjugation by G acts on the primitive idempotence of Kn in this way. And this gives us this rule for these elements that are generating this subalgebra. And this rule is telling us that this subalgebra is going to be finitely generated as a module over the ring of integers OK. And it is not difficult to see that this module is going also to be free. And it is, we can see also easily that it will be a Hopf order of Kj over OK because the form of the co-multiplication, the co-unit and antipode of a primitive idempotent an with n with nu in a nu with nu in n hat. Okay. And the key point comes here. So Kn is N is an abelian subgroup, so Kn is a commutative algebra, semi-simple commutative algebra. So it decomposes as the direct sum of copies of K, so many copies of the size of N. And L is a subgroup of N, okay? This is an hypothesis that we did not use yet, and now we are going to use it. So KL is a subalgebra of Kn, so this means that any primitive idempotent of KL will be a sum of primitive idempotents of Kn. Okay, so that makes sure that X contains all the primitive idempotents of KL. And once we have that, our previous expressions for J and J inverse make sure that J and J inverse belongs to X tensor X, so that we can apply the twisted procedures and we are done. So that is the end of the proof. So just two final comments. We characterize the Hopf order that in our paper, we characterize the Hopf order that we constructed as the unique Hopf order containing the primitive idempotents of Kn. And also in our paper for certain semi-direct product of groups, we were able to prove that this Hopf order is the unique one. So that's it. Thank you very much for attending and attention.
So my question is about whether you see the possibility of extending this result to Hopf algebras. Of course, you don't have Moshev's strategy for constructing cocycles, but some of the objects seem to have a natural generalization. So do you think you can extend some of the philosophy?
We thought about extending to. We thought about relaxing the hypothesis on Kn, on N. We thought about taking it further to solvable or something like that. Mm-hmm. We thought long on this, but we did not know how to overcome this technical point 3 to somehow make that the Hopf order have elements which swallow the fraction. Mm-hmm. So that was, so if you see here, the point here is that the fraction is going to be hidden in this primitive idempotence. Mm-hmm. Okay? And that makes sure that the element, the twist is going to belong to the Hopf order with itself. But this relies on this very technical hypothesis, and we did not know how to avoid that. But it could be very nice if we can take this result further to other families of groups. But the point is that is the point, that you have to deal with the fraction, and what we are doing here is that we are constructing a basis such that the element in that basis swallow the fraction, and when they multiply, all the structural constants are in a number field, in a number ring, sorry. So indeed, in this case, they are indeed in the integer, in the usual set. But we don't know. So very little is known about this. Indeed, there was a last question here. The only examples of Hopf orders we have so far are in this way, arise in this way. So we don't know any other way to produce Hopf orders that do not come in this way. Okay. Thank you.
Is Yevgenia Kashina from DePaul University. Unfortunately, she was not able to come to the meeting, and her talk will be given by her co-author, Jörg Sommerhauser. And the title of the talk is Jette Drinfeld Hopf Algebras, Byproducts and Extensions. Please.
I would stand like this. Okay, all right, thanks. Everything fine with the camera? Everything fine? Okay. So, first of all, I'm sorry for this. So, Jenny and I originally had planned to give 2 consecutive talks on our joint work. She was supposed to give the first talk, and I was supposed to give the second talk. She is sick, unfortunately. She cannot come. She sends her regards to all of you. And I'm now kind of giving her talk too, so you will hear me twice on more or less the same topic. Well, of course, not the same talk, but yeah, here we go. So let me first point out some references. So we have here this is her old paper on the classification of dimension 16, which was already mentioned in Taiki's talk. There were 2 follow-up papers on that, on semi-simple Hopf algebras of dimension 2 to the power m, and a second one of the same type. And then we constructed first a certain Jette-Drinfeld Hopf algebra, and then from there the corresponding Radford byproduct, which has dimension 32, as I will explain, and therefore is of dimension 2 to the power 5. And then the question that we were planning to discuss, or will be answered in this talk is this new Hopf algebra that I'm going to define, does it fit into the scheme that Genia developed in her papers before? And the answer is no. And I will explain why this new Hopf algebra is not of this type. We have by now 3 papers out on this one Hopf algebra, well, on this very small family of Hopf algebras of dimension 32. But there is still new material, and what I will tell you in the second talk is not in these papers yet. But okay, here we go. This is how the thing is. So I will first discuss Jette-Drinfeld Hopf algebras in general. Then I will give you the specific example, which is a Jette-Drinfeld Hopf algebra of dimension 8 over the Klein 4 group. Okay, so it's not cyclic. Then I will discuss the Radford byproduct construction in general, and then apply this to our situation, which then gives byproducts of dimension 32. An 8-dimensional Jette-Drinfeld Hopf algebra over the Klein 4 group, 8 times 4 is 32. And then the key question is, it's more standard for most of the people working in this classification business to present Hopf algebras as extensions of Hopf algebras. So we worked out all possible ways how this Hopf algebra can be written as an extension, and I will review that. So what are Jette-Drinfeld modules briefly? This Jette-Drinfeld module, so you have a fixed Hopf algebra H, and you have a left module and a left co-module over this fixed Hopf algebra H, but they have to be compatible. And the formula says if you first act and then co-act, you can rewrite this by writing this as first co-acting. You see the upper indices here, and then doing something more complicated, but in particular involving the action here. I want to warn you, because I'm a little bit crazy, this is it's a left co-module, so this is an H component, this is a V component. Many of you will use negative numbers in this point, which I do not do. So more precisely, these are left Jette-Drinfeld modules, right Jette-Drinfeld modules will appear and are defined in a similar way. So what does this mean if you have never seen this before? In the case where our Hopf algebra is the Hopf algebra over a group, the the co-modules, as Steph already reminded us, are just G-graded vector spaces. So we have a G-graded vector space on which G acts, and the compatibility condition says that the action with a group-like element takes the homogeneous component of degree G into the homogeneous component of degree G, H inverse. Why is that? If we have a homogeneous element of degree G, then we write down this compatibility condition that was on the previous slide already. And now this here, this is group-like, so this becomes H and H inverse. This here is the degree. This becomes G because V is in GH. And here you see the corresponding action over here. So this means that the Newman element has degree H, G, H inverse as required over here. Yeah? So this is what it says. So there are basic operations on the Drinfeld modules. Of course, you can take the direct sum of two, but for us, more interesting is the tensor product operation. They form a braided tensor category, as I will explain in a second. But so we just have the diagonal action, and then we have the co-diagonal co-action, and here you see, again, my obnoxious index convention. This here is an H, okay? So you can multiply two of these elements together. And there's also a quasi-symmetry or a braiding. It goes like this. So you take the H component. So while the V passes the W, the H component of V kicks. Yeah, usually I kick somebody in this situation, but you are too far away right now, so I kick the chair. The H components of the V kicks the W, and it's like this. So why is this way of defining the braiding or the quasi-symmetry, why is it better than just interchanging the two tensor factors? Well, the reason is that this way, if you define it in this way and not in the more canonical way where this factor is not there, then the morphism becomes linear and collinear over the, so it's a morphism in the category, where it's in the other definition this is not the case. Let's briefly check this. So if this is proof the H linearity. So if we first act, then by the definition of the action that I had on the previous slide, I do this. So then I have to take the H component of this and act on this. This is this formula. Here you see the H component of this, and here you see the other guy, and here's the other component. And now you can use exactly the compatibility condition that I had. Compatibility condition becomes this. This is just copied. This goes up because this is has now 3 copies here. This goes up 2. And then you see that these two terms cancel. Because this term cancels against this term, we are left with this formula over here. And this is exactly H acting on the quasi-symmetry. If you act on this diagonally, you see this. Okay, so this proves the H linearity. This is why this morphism is better than just the flip map over here. So what are yet the Drinfeld-Hopf algebras? We have discussed it in this context quite often. They are just Hopf algebras in the braided monoidal category of Drinfeld modules. Just you can write the axioms for Hopf algebra in an arbitrary tensor category because they are all only diagrams. And if you do this in the Drinfeld category, you get this. Let's unwind a little bit what this means. So this means that first of all, it's an object in the category, so it's the Drinfeld module. But secondly, there needs to be a multiplication. And this multiplication needs to be a morphism in the category, so it's H linear and collinear. And there's there's also an H linear and collinear unit map, so that, but the diagrams then say that this is an ordinary algebra in the category of vector spaces. So there's nothing happening. It's just an ordinary algebra with additional structure. This is so far this is very boring. On the co-algebra side, there's also nothing else happening. So we have an H linear and collinear co-multiplication, which goes to the other goes in the other direction. And an H linear and collinear co-unit map that goes down to the base field. But the axioms, the diagrams just tell you that this is an ordinary co-algebra in the category of vector spaces with respect to these structures. So it's just a co-algebra with additional structures. So far, pretty boring. But the music plays in the assertion when I say the co-product and the co-unit are algebra homomorphism. This is not very interesting for the co-unit, but for the co-product it says that the following diagram commutes. So you first multiply and then you apply your algebra homomorphism. This is delta, yeah? But then you have to apply the algebra homomorphism first and then you multiply. But how do you multiply? The multiplication here takes is the product. We have seen it in Marcello's talk already. This is the duoidal structure here, so to speak, on the thing. It interchanges these two middle factors. So here you have the quasi-symmetry from the preceding slide at this point. This is the multiplication in A tensor A. You first interchange the middle factors and then you multiply them together. So, and this in particular tells you that Jeter-Drinfeld Hopf algebra is not an ordinary Hopf algebra. This only happens, in fact, this is if and only if this sigma is the ordinary twist, the ordinary flip, I wanted to say. And finally, this is also not boring, not interesting. So there is an H-linear and collinear map SA called the antipode, which satisfies the standard antipode equations. So this is nothing new from the point of view of Hopf algebras. Only this commutative diagram is new. Now the goal is to construct some examples of this, and there are several. In the sequel, I will now, from now on, everything is algebraically closed of characteristic 0. So then we have fourth roots of unity. Zeta can be arbitrary, so it could be -101, in which case it's non-primitive, but iota is kind of the primitive fourth root of unity, which is unique up to a sign now. So, and then I take two commuting generators, x and y. So they commute from the beginning, and I introduce the following relations. X to the power 4 is 1, and y square is equal to this. Okay, yeah, this is the definition. Please note, zeta appears here, iota does not. Iota does not enter the defining equation, okay? So, and then I introduce two automorphisms on this algebra. So I map x to x cubed and y to x cubed times y. And you can check that these two elements again satisfy these relations. And you can do this with the second automorphism, which is defined on the generators by these equations. They also satisfy these relations. This is even easier to see. And then we see that we get a basis of A. So the basis looks like this. The dimensions of this algebra is 8. A basis consists of the following elements. This is, there's an easier basis, but I use this one. So you start with the unit element. Then you form this linear combination here of x and x cubed. And the scalars are here built from this fourth root of unity that I have. Here is where iota enters, okay? Yeah, at this point. And the other ones are defined similarly. Omega 4 is just x squared. And here you have this, again, another linear combination of x and x cubed, so that these two together span the same space as x and x cubed. And then you have here the multiples of y times the various powers of the x's. Okay, you see this? So now this is the basis. And then the co-algebra structure on this algebra is defined by requiring that these basis elements are group-like elements. Okay, so this fixes the co-algebra structure. So it's co-commutative in particular, which is was one of our goals. And the group that is here in the background now is the Klein 4 group. Z2 times Z2, where we're using these abbreviations. This is the 0 element, the canonical basis vectors, and the remaining element over here. Yeah. So, and then we have to introduce an action, and I had told you already two automorphisms. One, the automorphism phi, this gives the action of G2, and the automorphism phi prime gives the action of G3. And these to generate, of course, the group. So this describes an action of the entire Klein 4 group here, what I've specified here for the basis vectors x like this. And then the etas form one G orbit. This is important from some perspective. This is one G orbit of length 4. We have this here is a G orbit of length 2, and we have two fixed points of the action, namely the unit element and omega 4. Yeah. So the coaction is derived from the action by a technique that also showed up in Taiki's talk already. If you have an R matrix, you can derive from an action a coaction, and the whole thing gives you a Jeter-Drinfeld module. You discussed this in general. I discussed only a special case of this. So with the coaction is so that the fixed points are also co-invariant. So this means that this is the coaction here. Omega G1 is the unit element. And here you see we have, again, a linear combination. So omega 2 and omega 3 are not homogeneous, but rather go like this. And so this gives on the omegas the coaction. And to understand the coaction on the etas, it's a little harder. For this, we define a certain bicharacter, as in Juan's talk a second ago, by requiring that after all, the Klein foregroup is a two-dimensional vector space over the field with two elements. And so we can talk about bilinear forms, or practically. So we specify them on the basis vectors. And it's plus and minus, has to be plus and minus 1 because everything has to be order 2. But this here so this here can be plus or minus 1 depending on whether zeta is primitive or not. Okay, yeah. So I squared is minus 1. Yeah. And then we define the coaction on the etas by this formula derived from this bicharacter over here. But this is really Taiki's formalism that he already explained. It's coming from a certain R matrix. In our paper, we do this in greater detail. Okay, the antipode is also very easy. It's so on here it's just the identity, and but quite remarkably, the antipode on eta 1 on this group-like element. In Jeter-Drinfeld Hopf algebras, the inverses of group-like elements are not group-like again. Okay, so you see this very explicitly. So this is not one of the etas. It's a linear combination of the group-like elements, like this. And if you know this, you can kind of derive the other things by H linearity. If you have an element that takes this to this, then these two terms need to be interchanged. And these two terms need also to be interchanged. And then the remaining formulas come about by just considering linearity. So this is the antipode. And so this is now, at this point, I have constructed the Jeter-Drinfeld Hopf algebra over the Klein foregroup completely. Okay, I've told you all the structure elements. There is a second example of a very similar nature, which I will mention only very briefly. This is generated by two non-commuting, before they were commuting, two non-commuting generators, x and y, subject to very similar relations. X to the power 4 is still 1. Here you see the non-commutativity of the two things. Yeah, they do not commute. And here you have a very similar but slightly different relation for y squared. It's not the same as before, but it's very similar. And also the other structures are very similar. This is the only thing that I'm going to say about this. But you see this is co-commutative but non-commutative. Before we were commutative and co-commutative. Okay, so this was the setting there. So as Taiki already reviewed for us too, to every Jeter-Drinfeld Hopf algebra, you can associate the corresponding Radford biproduct. I'll briefly review this thing too. So the underlying vector space is A tensor H, and in all my papers I use this notation, but Genia stopped me from doing that. So, but the multiplication here is the smash product. You see again, it's not the ordinary tensor product of two just component-wise multiplication. Rather, as the H passes the H prime, the H kicks the A prime with its left leg. This is the left leg of H. Here it kicks this. This is how this is. And the co-multiplication is strictly dual to this. And here you see this, what I also call the co-kick. This is the co-kick. And Peter Schaumburg always asks me, how will I co-kick? I demonstrate the co-kicking in the same way as you demonstrate the kick, but I haven't figured this out yet, okay? So, so this is and because this is carries non-standard structures, we in our new papers avoid writing the tensor product here, but rather write a star in order to indicate that we have modified multiplication and co-multiplication on this tensor product. Okay, now let's see if we apply this construction to our Jeter-Drinfeld Hopf algebra, we get a Hopf algebra of dimension, Jeter-Drinfeld Hopf algebra is dimension 8, Klein foregroup has dimension 4 or order 4. So the tensor product has dimension 32. And it's, of course, generated by by 4 elements, namely the elements that come from the Jeter-Drinfeld Hopf algebra that are now denoted by U and V. And the corresponding generators of the Klein foregroup are now R and S. Okay, so these are the 4 generators. Please keep this in mind. These 4 letters will now appear all the time. Okay, and this is the definition. These are the generators of this algebra. And then you can convert the defining relations for x and y that I just showed you and the Klein foregroup into defining relations for these guys. These are the relations that come from x and y, just rewritten in terms of u and v. These are the defining relations for the Klein foregroup. And these are the defining relations that arise from the Jeter-Drinfeld, from the interaction of the two things. Yeah, the kick formula that I just showed you that leads to these relations. These are the 3 set of relations. And then the co-product, you can work the formula, the co-kick formula that I just showed you works. You can go compute, of course, because these generators come from the Klein foregroup. They are group-like elements, R and S. And the formulas for U and B, the co-kick formula leads to these 2 rather involved formulas. Okay, but it's a linear combination, but then definitely not group-like. Yeah. Okay, so this is the definition of these Jeter-Drinfeld Hopf algebras and the Hopf algebras. We have seen this now, and for people working in extension theory, it is of course more plausible to work or to look at this from the extension point of view, and this was also necessary to compare it to Genia's previous work. Okay, yeah, on the topic, and so we now figure out all possible ways. To write these as extensions. And this is possible in 4 ways. There is a unique 16-dimensional Hopf subalgebra of this 32-dimensional Hopf algebra, which we call N. This is called N. And it is isomorphic to the Hopf algebra HD11, which also showed up in Taiki's talk already. And reference 1 is Genia's paper on if you recall the first slide, it is Genia's paper on dimension 16, the classification of dimension 16. So it's neither a group algebra nor a dual group algebra. It is normal. Did I say that? Yeah, here. And therefore B fits in exactly one extension of the following type that you see here with dimension n equals 16, and the quotient has then dimension 2. Okay, must be the 2. Yeah, okay. So this extension is, of course, not an abelian extension at all, so it doesn't fit into Genia's previous program for this reason. So in particular, we see that B does not contain a commutative Hopf subalgebra of prime index. So this was always the case in Genia's previous papers where this was the classification start. Okay, so it happens that that N also arises as the unique 16-dimensional quotient of B. Same Hopf algebra arises as a quotient. And the quotient map is co-normal. And because there's a unique quotient like this, this means that B fits into exactly one extension of the type U. And here's this quotient map pi n, which will reappear later, where U has dimension 2 and the quotient has dimension 16 now. This extension, of course, is also not abelian. Can you write the Hopf algebra as an abelian extension? The answer is yes, and you can do this in 2 ways. So it turns out that B has 3 Hopf subalgebras of dimension 8, which we call M1, M2, and M3. Fantasy is limited, okay, yeah. So and M1 is just the span of the group-like elements. So it contains group-like elements order 8. And the other ones are isomorphic to the dual group algebra of the dihedral group of order 8. Yeah, dual group algebra of this ring of functions on the 8. Only M2 of these 3 is normal. And this means that B fits into exactly one extension of the type MBQ, where M has dimension 8, and therefore the corresponding quotient Q has dimension 4. Okay, yeah? Keep in mind 4 times 8 is 32. And of course, I said already M2 is isomorphic to this. This was already said. And the corresponding quotient, there are not so many Hopf algebras, semi-simple Hopf algebras of dimension 4. So this must be KZ2 times Z2. This extension is, of course, abelian, but it is not central or co-central, so it's also not of the type that Genia considered in her previous papers. Yeah, this is in a sense, has different properties. Similarly, B has 7 sub-Hopf algebras of dimension 4, but only one of them is normal. And this means also that B fits into exactly one extension of the type PBF, where P is now 4-dimensional, and the corresponding quotient is therefore 8-dimensional, okay? Yeah? Only one of them is normal. And in this case, it's the other way around. The P is Z2 times Z2. This is self-dual. And here you have the dual of the previous dual group ring. It's the group ring of D8, the dihedral group of order 8. This extension is, of course, abelian, but also, again, neither central nor co-central. Okay, so these 4 ways are the only ways how you can write this as an extension of Hopf algebras. Okay, this is now completely finished. And to end this talk, Genia's talk, I will briefly discuss one other question. I showed you at some length the definition of the Jeter-Drinfeld Hopf algebra A, which was commutative, and then I flashed very briefly Jeter-Drinfeld Hopf algebra A prime, which was not commutative. Of course, you can apply the Jeter-Drinfeld Hopf algebra construction. They are obviously not isomorphic. One is commutative, one is not commutative. But you can also apply the Redford biproduct construction to A prime and get a biproduct called B prime. It has also dimension 32. And the question now, so the Jeter-Drinfeld Hopf algebra A prime on the second example is not isomorphic to A, because, as I said already, one is commutative, the other is not commutative. However, the Redford biproduct B prime, which is the Redford biproduct of A prime and H, arising in the same way, this is isomorphic to B. And the isomorphism, I do it in the other direction here because it's written down a little simpler, goes like this. If you denote the corresponding generators by prime over here, then it goes for, then the mapping is defined like this. R prime is also defined the similar way, but in the H part, so to speak, it's just the identity in a certain sense. So this is the corresponding formula. This gives you an isomorphism, and therefore we will not consider, well, not in great detail anymore, this B prime because it's just isomorphic to B. All right, this is the end of this first talk of Genia's talk. Thank you very much.
B is self-dual.
This is the subject of the next yeah.
So B prime, the A prime is the dual of A in the category of heterodimensional modulus.
You must use the microphone.
No, I don't think so, because A is commutative. So A prime is commutative. A prime is not commutative but co-commutative. So if you dualize that, so this cannot be self-dual. No.
I am asking you, one is the dual of the other.
No, A is self-dual. I will discuss this in the next talk. A is self-dual. And so, yeah, well, A prime we haven't. So you are absolutely right. There's the dual of A prime, which does not appear so far in the discussion. No. So, but A is self-dual. I will discuss in which sense this is the case. B prime is isomorphic to B, and we will see that B is self-dual too. So this does not happen. But the dual of A prime is not in the picture yet, so to speak. But A is self-dual.
Thank you.
Yeah, we will discuss this right now.
Say that A is commutative but not co-commutative?
A is commutative and co-commutative.
Ah, okay.
So again, A is commutative and co-commutative. A prime is not commutative but co-commutative. Both have a basis consisting of group-like elements, right? The etas and the omegas, these are group-like elements and form a basis. So it's isomorphic to a group algebra as a co-algebra.
is dual to the previous speaker in a commutative way. So Jörg will give his second talk, self-duality of Jeter-Driefeldt-Hopf algebras and their byproducts.
Thank you very much, Steph. So I had now Nicolas, Marcelo, and Steph all had comments on the same question now, which is addressed in the second talk, okay? It's a very interesting question, obviously, because it triggers a lot of discussions. So let me give you two additional references, which are very old. So this is my diploma thesis, and this is my PhD thesis, okay? Yeah, so, but I'm putting these references up because at the beginning of these and most other papers, I explain the same stuff, namely how to dualize in the category of Jeter-Driefeldt modules. This is always at the beginning there. And this is already quite subtle. So this will be the discussion at the beginning. Then we will dualize the Jeter-Driefeldt algebras that I just showed to you. Then we will see how this dualization discussion applies to the Radford byproduct. And then we will see that we'll see the dualization of the Radford byproduct in our case. Turns out to be self-dual, Nicolas, as answering your question, so to speak. And then in the second part of the talk, everything is semi-simple, so I will discuss the Wedderburn decomposition of the Hopf algebra here, which is also quite remarkable in a sense. And then we will discuss, remember, we had the choice, the Hopf algebra depended on the choice of the fourth root of unity, zeta. Not really on iota, but on zeta it depended. Do different choices of the root of unity affect the isomorphism type of the Hopf algebra? I will answer that question. Okay. First of all, let's recall from the previous talk by Evgenia that B can be written as an extension in 4 ways. In one with dimension 16 and one of dimension 2 in the quotient, and then the other way around, 2 by 16, or the other way around. But as Nicolas already saw, this suggests that this algebra may be self-dual. In particular, if you compare it with the other 2 forms, where you have dimension 8 in the kernel and dimension 4 in the co-kernel, and there's an exactly dual one, so to speak. So this raises the question of whether this Hopf algebra is self-dual. So, and how do you want to approach this? You may try to show first that A, the Jeter-Driefeldt Hopf algebra is self-dual, and here the question arises, what does that really mean? Okay, what does that mean? Okay, so this is the part of the first talk. So, and you learn, I have been preaching this for decades now, okay? So this is my sermon here. So if you have a finite dimensional left, you have Jeter-Driefeldt Hopf algebra, and let's forget that you can do this for a bi-algebra, okay? You can write all the axioms down. Let's forget that we have an antipode for a second. Then you can dualize this, but it becomes a right Jeter-Driefeldt Hopf algebra. The sides change. Over H, and here are the definitions. The actions on the right is just dual to the action on the left on the dual space. And in the co-action, it's the same, and here I'm confusing you again with my index convention. Here this is on the right, so this is in H, and here this 1 is in H, okay, because it's a left co-module. Right co-module has 2 in H, left co-module is 1 in H, very sneaky, okay? But this is the definition here for these elements here. So therefore, okay, and left Jeter-Driefeldt modules are right Jeter-Driefeldt modules over H opcop and vice versa. So this takes you away. So the A star is therefore a left Jeter-Driefeldt Hopf algebra over H opcop. Okay? Yeah? So now if H has a bijective antipode, then you have 2 ways of making H opcop isomorphic to S, namely the antipode and its inverse. And if you pull back the structures along these two isomorphisms, you get two duals. One is the left dual, and one is the right dual in the categorical sense. This is how this works. So, in other words, the question of whether A is self-dual or not is not even well posed. You can say it's isomorphic to the left dual, or it's isomorphic to the right dual, okay? In our case, this is what I say here, sorry. However, in our situation, this does not play a role because we have S is equal to order 2, or exponent 2, I want to say, and so the antipode is the identity in the first place, yeah? So all these things are not seen here. But okay. Let's see this, self-duality in our cases. And now I say again what we just discussed over the break between the two talks. The second Drinfeld-Hopf algebra is not self-dual because it's co-commutative but not commutative. This, Nicholas, was also your question. The first Drinfeld-Hopf algebra is self-dual, but the construction of the isomorphism requires the separate discussion of three cases. First, this fourth root of unity is primitive. Second, the fourth root of unity is -1, and then, which is not primitive, it's a fourth root of unity, fourth root of unity, and then it can also be equal to 1. These three cases need to be discussed separately in the discussion. All three cases, all the discussions are very similar, so in order for time considerations, I do only the middle one, but it's very similar, okay? I discuss now this case where zeta is -1. It's kind of the intermediate case between the two situations. Okay, then we have characters, and to split this in Juan's terminology, this doesn't split over the cyclotomic field of order 4, but only over Q8, so to speak, yeah? So you need a primitive 8th root of unity, and you choose it so that the square of it is the primitive 4th root of unity that is already in the game. This is now called Xi for the rest of the talk. So please, this Xi appears now frequently. It's a primitive 8th root of unity satisfying this equation over here, yeah? So, and then we define 8 characters, epsilons and rhos, by requiring that we had 2 generators, commuting generators x and y, and we require that our 8 characters, epsilons to the rhos, take on our generators x and y these values, okay? So this is here you see the 8th root of unity appearing, okay? This defines 8 characters. I'm not going over the computation, but these are all. And then the isomorphism is given very easily by this formula here. So you map the etas to the rhos, and you also map the omegas to the epsilons. Why did this strange guy? I can count in principle. This is 1, 4, 2, and 3. Why is it in this strange order? Because these are the 2 fixed points. These are the orders of length 1, the orbit of length 1. And this here is the orbit of length 2, so these here are kind of connected, so to speak. This is why it's written up in this slightly strange form. And here I really prove that I can count 1, 2, 3, 4, okay? Yeah. This is the isomorphism. This is an isomorphism of your Drinfeld-Hopf algebra, so you can do that. Okay, then there's a second dualization. Now, if you have a right Drinfeld-Hopf algebra over a finite dimensional Hopf algebra H, this is now back to the general setup. Before A was finite dimensional, now H is finite dimensional. Yeah? It's a dualization of a second type. You can turn it into the same Drinfeld-Hopf algebra into a left Drinfeld-Hopf algebra over H star, with respect to the following structures. So an element from the dual space of H acts on this by taking the H component, this is the H component, it's the right comodule, and multiplying it like this. And for the comodule structure, you take the following formula. You take a dual basis of a basis of H, it's finite dimensional with this corresponding dual basis, and then you let the base elements act on the right. and take this as the corresponding H part, H star part, I wanted to say, sorry. And this turns it into a left, 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 Jette Drinfeld module over H star. So now how do you dualize byproducts? So suppose now that you have a finite dimensional left, left Jette Drinfeld Hopf algebra over H. Then by the process that I explained on the first slide, the dual turns then to a right Jette Drinfeld Hopf algebra. Yeah? And then you apply this is the first dualization, then you do this second type of dualization that I explained on the previous slide. And so A star is now a left-left Jette Drinfeld Hopf algebra over H star. And this means that you can form this byproduct in the way that I explained before. And it turns out that the canonical map that you have here, the canonical map, this is a Hopf algebra isomorphism, okay? And if you, this is A, yeah, I think you see this. Okay, so and this implies, therefore we see now, if we apply this to our situation, we have constructed an isomorphism from A to A star of left-left Jette Drinfeld Hopf algebras over KZ2. This was the slide with the epsilons and the rhos and where the etas and the omegas go, which I showed you on the previous slide. Now, of course, the Klein-4 group, we are in characteristic 0 algebraically closed, this is self-dual, okay? Yeah, well, this is exactly characteristic 2. It's anyway self-dual. But, so there is such a Hopf algebra isomorphism, no question. But you can show that you can choose it in the following way. The left action here can be pulled out so that it becomes the corresponding action of H star that I introduced on the preceding slide. You have to do that, okay? Yeah? And with the coaction, it's the same thing. If you apply the coaction to the dual space that I explained before, it's computed from the ordinary coaction, which is in H tensor A, by applying these two maps. So you can choose this psi in this way. And therefore, the tensor product, if you now go over all the formulas, the tensor product of the two is an isomorphism between the two byproducts, yeah, B and B star. Why do I see two byproducts? Because B star is A star tensor H star by the preceding slide. So in other words, this answers your question, Nicolas. So the Hopf algebra is self-dual, okay? This is the answer to this. And B prime was isomorphic to B, so this B prime is also self-dual as a consequence, although this does not work for A prime, okay? Yeah. Okay, so this finishes with the first part. Now, the whole thing is semi-simple, so everybody wants to know what the Wedderburn decomposition is. You can do this by dimension count. This is not super complicated, but we need it for other purposes. To investigate this further, we needed to construct the simple modules explicitly. This is what I'm showing you now. So B is semi-simple, and its irreducible representations look as follows. There are 8 one-dimensional representations. We have already seen that already said that the group of group-like elements has order 8. It's elementary abelian, Z2 times Z2 times Z2, self-dual. So this means that we have 8 one-dimensional representations. There are 2 two-dimensional representations and 1 four-dimensional representation. It's just sort of remarkable that this appears. But okay, so let's do the dimension count. 8. Four-dimensional representation has a four-dimensional Wedderburn block. 2 of them give 8 dimensions, so 8 plus 8 gives 16. And then this is a 4 times 4 block, has dimension 16. 16 plus 16 is 32, so the dimensions match, okay? Yeah? All right, so let's see how these things really look. So recall, these are our generators. I showed you the defining relations before. The one-dimensional representations are, of course, the group-like elements of B star. This is always the case, and therefore you know that there are 8 of them. And this is the isomorphism type, but this is a consequence of this self-duality. And so in other words, this here is a 3-dimensional vector space over the fields with 2 elements, and you can pull this back, and then you have corresponding generators over in G star. And these generators here, this is the only thing that I'm telling you. I'm not giving you a table of all 8. I'm only giving you a table for the generators and the corresponding products that arise. And here you see my 3 canonical basis vectors in quotation marks. And here are the values that they take on the corresponding generators. It's only plus and minus 1. It's very explicit, but the details don't matter. So how do the 2-dimensional representations arise? This is already in our second paper. Remember that we can write B as an extension where the 16-dimensional Hopf algebra appears as a quotient. And I said already, or Genia said in a previous talk, that this is isomorphic to the Hopf algebra HD11 in her dimension 16 classification. And you can look this up in her paper. This has she explicitly constructs this. There are 2 two-dimensional representations, and these you can pull back along the map pi n to 2 irreducible representations of B, because this is surjective, this stays irreducible. Yeah? Okay, for the first 2-dimensional representation looks then, if you do this, it looks on generators like this. On the generators U and V, you get these 2 matrices. And on the generators R and S, you get these two matrices here. This is actually the identity matrix. And the second 2-dimensional representation looks on generators very similar. So you have, this is U and V again, U and V. And on the other generators R and S coming from the client 4 group, you have these 2 matrices here. Okay, now the 4-dimensional representations is again like this. So you have to go over the cases zeta primitive, zeta is equal to -1, and zeta is equal to 1 separately. And for time considerations, I only show you the middle case that I also focused on before. So we have now zeta is equal to -1. And recall that from the isomorphism discussion that I had before, I had shown you that there is a 1-dimensional character which I denoted by ρ1 at this time, and I showed you the values on the generators. So on A, on the generators X and Y. And of course, if you have a 1-dimensional character of an algebra, you can use this to turn the base field into a 1-dimensional module over the algebra. Yeah, this is what you do. And then you can induce this up. So you take B of dimension 32, induce it up over an 8-dimensional algebra here. This will give you a 4-dimensional module. Yeah, this is Clifford theory, of course. Yeah, this is 4-dimensional and irreducible. And you can also work out the matrix description. Because of the induction procedure that I just explained, this is isomorphic to the group ring of, as a vector space, this is isomorphic to H, which has the canonical basis from the client 4 group. And so these are the corresponding basis elements in the induced module. And with respect to this, the matrix representation is like this. Rho is a 4x4 diagonal matrix with iota plus minus in the entries, and here you have this primitive 8th root of unity whose square is iota showing up again. Yeah, this is the same one that I had before. And the 2 other ones are non-diagonal. Rho R and S look like this, but this is kind of easy to see. This block diagonal of order 2. And this here is kind of also block matrix in another sense. But you see that this has order 2 matrices, as it has to be. Yeah. Okay, so this is the pretty explicit description of the irreducible representation in specific bases. This finishes the discussion of the Wedderburn decomposition, and then the last question that I want to address is. So we have the whole construction does not really depend on iota. This is just how we put the group, how we figure out the group-like elements. But zeta is an essential ingredient. So you can choose 4 values for zeta. So the Jeter-Drinfeld, the definition of the Jeter-Drinfeld Hopf algebra depended on a 4th root of unity zeta. And to mark this dependence, I now call it a zeta because I want to vary zeta. And then, of course, here we have, if I take a different zeta prime, then the 2 Hopf algebras are not isomorphic. Why? This is not hard to say, not hard to see. However, there is always an isomorphism between the corresponding byproduct, B zeta, and B negative zeta, which is also a fourth root of unity. So this matches the two primitive ones, and plus and minus one. They match under this correspondence. And I just tell you how this goes on generators. You map U here to U cubed here. V stays the same. R goes to SR, and S also stays the same. This is an isomorphism from here to here. But if zeta and zeta prime are not, so if one is primitive and one is not primitive, so zeta prime is plus minus 1, then the two Hopf algebras are not isomorphic. So this is in our new paper in the Bulletin of the Belgian Mathematical Society. It's not easy to see. I will briefly explain how this goes. So suppose that we have an isomorphism between the two byproducts, B zeta and B zeta prime. Then, of course, and this is the problem, this does not preserve the byproduct structure. So the byproduct is kind of factorized into A and H, and you do not know a priori that the A part is mapped to the A part and the H part is mapped to the H part. You don't know that. So, but of course, you get another byproduct decomposition of the same Hopf algebra by just carrying it over. It's not the original one, but along this isomorphism, the original byproduct decomposition gives you a new byproduct decomposition. So now you know that f of H, this is a Hopf subalgebra of beta prime. It has dimension 4. And we have already figured out how many there are. So there are 7 of these. These are the, in an 8-dimensional vector space over Z2, you have 7 subspaces of dimension 4. That's what I say here. You have 7 2-dimensional subspaces over vector, or in a 3-dimensional vector space over the field with 2 elements. This is really what I should have said. So there are 7 2-dimensional subspaces. They have order 4 then over a 3-dimensional vector space over the field with 2 elements, which has 8 elements. Yeah. And you discuss them one by one, and by discussing them one by one, and I don't do all the details here, you can look at these byproduct decompositions, and this is quite some work, and but we can rule out that such an isomorphism exists. So this is the end of this talk. Thank you very much.
So the way to look at the self-duality, I think, is as follows. Okay. So you work over a finite-dimensional Hopf algebra. So, of course, what you have is, if you take a left-left Jeter-Drinfeld module, and you take the dual vector space, that is a right-right. Yeah, this is what you said. But what you have to do is the following. So Jeter-Drinfeld modules are modules over the Drinfeld double. Okay. Right? Yes. The Drinfeld double is a Hopf algebra. Okay. The category of modules over a Hopf algebra is rigid. Yes. And the duality there involves the antipode of the original Hopf algebra. This is explained very well in the Castle book. And but here, in our situation here, what you have is the Hopf algebra is declined 4, the group algebra of the declined 4 group, and is the antipode is the identity. So the antipode on the Drinfeld double is also the identity, I believe. Yes. And so then that solves the thing, so that you can just take the dual. Here there is, you are right in every respect, but it's not a counter argument to what I said. So why is that? So what I said before
here, so you do all this dualization, and if you do it with the Drinfeld double, so it is the rigidities, so the category of modules over the Drinfeld double is rigid, as you say. But this is just reflected in the fact that the category of the Drinfeld modules is rigid, and this is compatible with all this.
Yeah.
And so the braiding in the category of the Drinfeld modules is just coming from the R matrix in the Drinfeld double. And so you have categorical, these categories are just equivalent. So the dual in your sense is the duals that I have here. So I just broke it up into various steps, and you get a left dual in your category, in the category of the Drinfeld doubles, by pulling this back along S, and you get a right dual by pulling it back along S inverse. Okay, so you always have your left and your right duals. So your proposal is just arriving at the same situation in a slightly different way. And but this question here still remains, okay? You have to specify in general whether you look at a left dual or a right dual.
Ah, yeah, of course.
Yeah.
In general, that will be different.
Yeah, in general, yes, here not. Yeah.
Okay, some other questions? Yes.
This construction is what the prime 2. Your construction is related to the prime 2.
Yes.
What happens if you take another prime, for instance 3?
Very good question. I mean, as you know, I've now investigated for many years how commutative or co-commutative Drinfeld algebras over a Abelian group look like. There is my wonderful, I love it, my wonderful PhD thesis here, which is concerned with this. So we had to go away from the group of prime order, and this Drinfeld algebra was constructed, as you know, because you were the editor of this paper, to find an example that certain features that show up in this case, namely the triviality of the core, does not hold in general. The omegas are the core of the eta, of one of the etas. And the omegas, the core is not what I call completely trivial, because you see the omega 2 is moved. It moves to omega 3 under the action of the Hopf algebra. It's not completely co-invariant. So this was just an ad hoc example that we constructed in order to show that these features are no longer the case. It is very well possible that all this generalizes in a certain way to higher primes, and we definitely have to investigate this. So then we would get an elementary abelian group, and if P is 3, it would be order 9, so to speak, and there would be a very similar situation. But I think the subject, what's special about the prime 2 is that you can, the etas, which form a complete orbit, can map to themselves under the antipode, because in the setting where the prime is 3, I expect that is no longer the case. So you have to have maybe 3 sets of etas, but I do not know how the picture works. But I don't think it is as simple as here, where we can live with one orbit of etas, so to speak, and then have the corresponding core. These are the omegas. If you are with higher primes, you need more sets of etas, because the antipode needs to map them somewhere, and they cannot map them to themselves anymore if the prime is not 2. So this is my picture, but we don't know this yet. We will study this if I live long enough.
Thank you. Thanks.
Yeah.
Anything else? Then let's thank all the speakers of this
Okay, ladies and gentlemen, we are ready to start our afternoon session, which I am pleased to chair. And our first speaker is William Houtkiet from the University Libre of Brussels, and he's going to talk about partial Jeter-Greenfeld's model. Please.
Thank you, and thank you to the organizers for this beautiful conference. I'm really glad to be able to give a talk here. I will tell you about some joint work with Eliezer Batista and Joost Verkruijsen, who is my supervisor. So I work with partial actions and partial modules of Hopf algebras, and I will introduce them properly in a moment. But first, I want to tell you a bit where this presentation is going. So there is an algebra which is central in the study of partial modules over an algebra, Hopf algebra, and this is the algebra H-bar. I will see if this works. Yes. So this partial Hopf algebra H-bar was introduced by Marcelo Alves, Eliezer Batista, and Joost Verkruijsen in 2015, and they showed two structural results about it. First, it's a Hopf algebroid over some possibly non-commutative base algebra. And secondly, it can also be written as a partial smash product. So the goal of today is investigating a bit the relation between these two structural results, especially in light of the following theorem of Tomasz Brzezinski and Giselle Militaro. So this is not in the partial case, but if you take a braided commutative algebra in Jeter-Greenfeld modules, then the smash product becomes a Hopf algebroid over A. Right? So I can update now what we want to do. So we would like to say at the end of the talk that H-bar is a Hopf algebroid because it is a partial smash product. So to do this, we will need some partial module analog of this theorem. So in particular, we will want to introduce a category of what we will call partial Jeter-Greenfeld modules. I will first seem to make kind of a circular reasoning, because I will suppose that H-bar, I will use that H-bar as a Hopf algebroid from the beginning, but I will come back to it at the end, how we can remove this circular reasoning. So, good. First, I will tell you what are partial modules and what is this algebra H-bar. So let G just be a group. We will say that it acts partially on an algebra. So this partial action is basically a partially defined action. And the domain of each alpha G, we suppose that it's an ideal generated by a central idempotent of the algebra A. And then there are three conditions. First one says that the unit just acts as identity. The second one is there to make sense of the third one. The third one is just saying that whenever it makes sense, so on this intersection of domains, you have multiplicativity. And so the second axiom is just there to ensure that after you act with alpha H on this intersection, you end up somewhere where you can apply alpha G. Good. The 1Gs are the central idempotents that generate the ideal. So 1G will be a central idempotent in A. No, not necessarily. You just take some central idempotents. So one of the units should be one. That's the only thing, in fact. Good. This is partially defined, but you can extend it by saying, a G bullet A will be, first I will project into the domain using the central idempotent, and then I apply alpha G. So that way we get a globally defined action which satisfies these properties. So the first two are not shocking, I think. The third one is different. So instead of mixed associativity, you get this G bullet 1, which is the central idempotent floating around. And we will use this to define a partial action of a Hopf algebra on an algebra. So it becomes this. So I just translated it to Hopf algebras. This was already done a long time ago, I think, by Steph, among others. And so this gadget we will call partial module algebras. Good. Once you have such a partial modular algebra, we can consider a smash product. So this is the usual smash product operation. It's still associative if you define it this way, but not unital anymore. Because if you plug in b equal to 1, the problem is that this h1 bullet b will not just be trivial. This will not be trivial, so it doesn't reduce. That's why the partial smash product is defined as the left ideal generated by one tensor 1. And now this becomes a associative and unital algebra. Good. So the elements are of this form, which we abbreviate with just a partial smash h. So it's generated by these elements. Let's maybe look at an example. So here I took H, just the group algebra of the cyclic group of order 3. And this acts on a two-dimensional algebra generated by two orthogonal idempotents. And then I define G bullet E1 equal to 0, but G squared bullet E1 is E2. So there you already see it's not a global action, it's really partial, because acting twice with G is not the same as acting with G squared, right? And so the idempotents associated to G will be E1, because G bullet 1 is E1, and G squared bullet 1 is E2. And then the partial smash, so the full smash, you would expect that it's 6-dimensional, but here it's partial, and so it gets reduced. It's only 4-dimensional. Two generators vanish, because in this procedure of taking the left ideal. So.
Another question about
Yep.
1G. If you have 1G times 1H for H different from G, is this 0?
No, it can be something non-trivial. Yeah. Yeah, this is in the example I took kind of a simple situation, but you can get more complicated things. Good. So I spoke about partial modular algebras, but what are partial modules? So a partial module is a vector space with a kind of action of H on it, but instead of the usual mixed associativity, we replace it by two axioms of partial associativity. So how you should read this is, you can only join the A in the second axiom, you can only join the H and the K1 if the S of K2 is present. So you should have some witness present in order to be able to apply multiplicativity. This is so you have a category of partial H modules, and these are in fact governed by this algebra H par that I mentioned in the beginning. So how you obtain it, you take symbols bracket H for H in the Hopf algebra, and then you mod out relations that are coming exactly from these axioms, right? And then the category of partial modules over H will be exactly equivalent to the category of modules over H par. Good. The structure of this H par is best described with respect to a subalgebra, which is A par, and this guy measures, in some sense, how partial you can get. So these epsilons of H, if you would pretend that no partiality exists, of course they become trivial. But here, this A par can be quite a big algebra. So there are even examples of finite dimensional Hopf algebras that have infinite dimensional A par. So this is a subalgebra, which is a partial modular algebra. So you conjugate with the bracket. This is a partial action. And then, with some work, every element of H par, so which is a product of these brackets, you can write it as an element of A par times a pure bracket. So this allows to see that H par is constructed out of A par and H, basically. More precisely, it's exactly this partial smash product. So this is one of the results that I mentioned in the beginning. This partial Hopf algebra, the H par, is isomorphic to the partial smash product of A par and H. Good. I also mentioned the other results, that H par is a Hopf algebroid, and this is over the same algebra A par. I will not describe the structure in detail, but a consequence of this is, of course, that partial modules become a monoidal category, where the monoidal structure comes from A-par bimodules. So this is nice, and especially the algebra objects in this category are exactly the partial modular algebras from the beginning. So terminology-wise, this works out. And I recall you what we wanted to do today is put an implication between those two theorems, right? And the reason we would like it to be that A-par is some kind of commutative algebra inside of a category of Jeter-Drinfeld modules. Good. So next step is to get to this category of partial Jeter-Drinfeld modules. It turns out, it's important to realize that the monoidal structure on partial modules is tensoring over A-par. But it turns out that if you take a global module, so a usual module, and a partial module, and you tensor them over K, over the field, you get again a partial module. So just by diagonally acting. So here X is my global module, M is my partial module, and on both sides you get again a partial module. So this means that the partial modules are a bi-actigory or a bi-module category over global modules. And so translated to our algebra H-par, this means that this guy is an H bi-comodule algebra with these coactions. In fact, there is a bit more, because we had this monoidal structure on partial modules, which was tensoring over A-par already. And we can see that partial modules form a pseudo-monoid in the two categories of bi-actigories. So concretely, what this means is that our monoidal product tensoring over A-par, the par is missing there, becomes a bilinear functor from this balanced tensor product of categories to partial modules. So bilinear means that you can kick out the global modules left and right. So the x's there are global modules again. I want to say these first two isomorphisms are less trivial than it looks, because the action of A-par on this X tensor M is a priori diagonal. So it's only because X is global that it only plays with M. So the first two are bilinearity. And then you have this balanced, which means that you can move around the global module on the other side of the tensor A-par. Good. And this is so the product. The unit of this pseudo-monoid is the following functor. So it's a strong monoidal functor from global modules to partial modules, which sends an X to X tensor A-par. And just like an R ring is in fact just a ring extension, this will induce completely the bi-actigory structure on partial modules. So at least for the left, it's already clear. Normally, if you tensor over A-par, maybe I should use a mouse. So if you tensor over A-par here on the right, then the A-par will disappear and you get again the left action. For the right action, I will come back to this in a moment. So we have this pseudo-monoid. We showed that partial modules, are a bi-actigory. So we can look at the relative center. So the relative center consists of objects together with a half braiding, which moves the left action of a global module to the right action. So this is a general definition, but in our case, both actions are just tensoring over the field. And this turns out to be equivalent to a category of generalized Jeter-Drinfeld modules. So where H-par now is this bi-comodule algebra. We look at H-par with this bi-comodule algebra that I showed. And this is really just Jeter-Drinfeld modules where you replace all actions by partial actions. Basically, this amounts to that. And so this category we call our partial Jeter-Drinfeld modules. Because partial modules form this pseudo-monoid inside of bi-actigories, we get, in fact, that Jeter-Drinfeld modules are a monoidal category itself, where the monoidal product is also tensoring over a par. I will show you how this works. So basically, the monoidal structure is inherited from partial modules. And so I will reason with these half braidings. So we want to move the X across, right? So you take M and M partial modules, the tensor product over a par, and then we use all of these isomorphisms that I described. First, you move in the X, then you swap. And then here in the middle, we use the balance property, so we can move the X, which is a global module, to the other side of a par. Then we swap again, because N is a Jeter-Drinfeld object, and we move out the X. So this will be the structure of the Jeter-Drinfeld object, well, of the element of the center, the relative center of partial modules. Good, so now we have a monoidal category. I forgot, I should explain why a par is in there, right? This is not obvious at first. So I already showed you how it is a partial module algebra. So this was by conjugating. So by conjugating here. And some calculation shows that you can write it as this product of two epsilons, not very important at this stage. And then you have a coaction that looks like this. So, and this will produce exactly this isomorphism between X tensor A par and A par tensor X that we need. And it's also only now that you can see why the unit of the pseudomonoid that I showed, so the functor that maps X to X tensor A par, induces the right structure, the right action. Because M tensor over A par, this X tensor A par, first you have to flip, and then only the A par gets eaten to produce M tensor X, which was the right action. Good. Unfortunately, there seems no way to see this gadget as a braided category, a braided monoidal category in any sense. This A par is just can be too asymmetrical. You only get braidings between global modules and partial modules, so in general, you cannot swap the two partial modules, which is annoying because we wanted to speak about commutative algebras in this category. But we figured that we could just put it there artificially for the theorem to work. So I will show you. In fact, we just require an algebra in this category such that, and this would be braided commutativity, right? AB, you swap the AB, which becomes B0 tensor B1A, and then you multiply. So this is the braided commutativity. And we just ask it locally. So we just want that for every AB this holds without having at disposal this map that really braids the whole category. And then we showed that indeed the partial smash product of A and H is a Hopf algebroid with base algebra A. Yeah, the proof is calculating a lot to show that it's indeed a Hopf algebroid. The structure is exactly the same as in the theorem of Tomasz and Gigel Militaru. So I put here some structure. Maybe a small remark that I can give is, if I'm correct, the article of 2001 of Tomasz and Gigel looked at Roux algebroids in some sense. You need a section map from H tensor over H to the naked tensor product. We use the definition of Gabi-Böhm with invertible antipode. That way you only have to describe one side plus some extra properties of the antipode. And we were more familiar with that. So it's maybe not exactly the same definition we used, but we still get this type of Hopf algebra out of it. Good. So now we want to apply it to get to our goal. I'm going to see how I'm on time. Okay. Great. So we want to apply it on A par, right? Because H par was the smash product of A par and H. So we want to see that A par satisfies this artificial braided commutative condition. So I recall here the structure. And one of the properties of a par is that you have equality between these two expressions here. And so this is what we will use. So if I calculate this, then first, here you have K3, K4. You move the S minus 1 K2, it disappears, and then you move this whole gadget also to the front and it will disappear. Yeah, this is here. So basically, yeah, it's a small calculation, but it works. That's the point. So we would like to conclude that indeed a par smash H is a Hopf algebroid by the theorem, except that, of course, I was speaking about algebras in Jeter-Drinfeld category, which is a monoidal category indeed, because partial modules was a monoidal category, but partial modules was a monoidal category because H par was a Hopf algebroid in the first place. So right now I've concluded that H par is a Hopf algebroid because it was a Hopf algebroid and a smash, partial smash product. So I've not really done anything, except that speaking about algebras and Jeter-Drinfeld modules was maybe not necessary, because partial module algebra, I defined it before even telling you what is H par, right? So if I formulate the theorem in a bit uglier way, like this, so I will just say I need an object in my partial Jeter-Drinfeld modules, which is at the same time a partial module algebra and a comodule algebra, which is just saying that it's an algebra in there, right? And then this extra commutativity condition, then I will have it. And now it's perfectly applicable to a par without knowing beforehand that H par is a Hopf algebroid. Good. I think I have a couple of more minutes. So we succeeded in our goal. I will just now, for the last 2 minutes, tell you a bit what we're doing more with this bi-actigree structure. So, as others have already mentioned, it's interesting to look at the right adjoints of the action functors. So tensoring with M is a functor from global modules to partial modules, which has a right adjoint. And the explicit form is what I wrote here. So it's an H par linear Hom of H tensor M. So this makes partial modules enriched over global modules. We can do the same thing on the other side, of course. And then you get a slightly different internal Hom. So partial modules are enriched in two ways over global modules. And then if you evaluate twice the same object, you will get an H module algebra, right? So these two guys are H module algebras with this composition. Good. Now it turns out that this internal Hom being a functor from partial modules to global modules, one could wonder is this some kind of globalization? So from a partial module, you create a global module. So we investigated this, and at least there are connections between them. So given a partial module algebra, you can consider the globalization of this partial module algebra, which is a module algebra. This has been described. On the other hand, we have these other algebras, and we also considered a third one, which is B bracket B a par, with some kind of convolution product. So now we have 4 H module algebras at hand. And it's not exactly clear yet, but at least in the case of finite group algebras, all of these coincide. So then the globalization of a partial module algebra over a group is exactly given by this internal Hom. So this we will investigate further to see if this generalizes to Hopf algebras or not. Thank you very much.
We have plenty of time for questions, please. Any questions?
Thanks. Thanks for the great talk. For the commutativity, did you consider one of 2 options, doing the Drinfeld center construction again and considering the object with the braiding now in the Drinfeld center of the twisted Drinfeld center, and the other option as a monoidal monoid, so the Ekman-Hilton argument.
We did not consider either of those. So you suggest to look at the center of partial.
Which then is braided monoidal. So you have.
I see. I will think about it. For now, I don't even have a good feeling what is the Drinfeld center of partial modules. This seems to be already quite complicated. But yeah, I will think about it. Thanks.
Thanks.
So when you introduced Jeter-Drinfeld modules, I thought that this was just the construction of the center.
Yes,
The
center with respect to the biactagory. So not internal, it's not with respect to the tensor product over A. You could also apply Drinfeld center to the monoidal category of partial modules, which would be something completely different, I guess.
Probably you said and I didn't get it. Your partial Jeter-Drinfeld modules can be really seen as actions plus coaction plus compatibility.
Yes, exactly. Yeah. So I will look for it. Yeah. So an object in this relative center is exactly a vector space with action, partial action, global coaction. Such that. So this is really, you take the definition of a Jeter-Drinfeld module over a Hopf algebra and you replace actions by partial actions.
Okay, thanks.
Hey, just a technical question. For the proof here, this is the same proof as for Jeter-Drinfeld modules? You take H, use the unit object and the braiding to get the coaction?
So in general, it works. I think this is something Joost and Ryan Aziz were also exploring. If you have even two Hopf algebras, a bi-comodule algebra, a bi-comodule algebra, and then you do this business. And this is the very special case where three of them are already the same. We look at only one Hopf algebra, and the bi-module co-algebra is just H2.
And can you do like a tetramodule constructions, like almost in Matti's talk, where we had tri-modules, and I mean there's a correspondence for Hopf algebras for tetramodules and Jeter-Drinfeld modules. So is there something like this here? Where
that I didn't think about. No, I have no idea. Thank you.
Okay, our speaker for the second talk is Laura Nastasescu, and the title is A Question on Frobenius Strongly Graded Algebra. Please.
So first I want to thank the organizers for inviting me to this beautiful conference. Okay, so the goal of this presentation is to answer to the following interesting question. If A is a strongly G-graded algebra where G is a group with neutral element E, and if A is Frobenius or symmetric, does it follow that the subalgebra given by the homogeneous component of degree E is Frobenius or symmetric? So I will start with a short introduction and some preliminaries, where I also explain the importance of the question, from where it started and its connection with the Picard group and invertible bimodules. I will start by recalling the definition of a Frobenius algebra. So a Frobenius algebra is a finite-dimensional algebra that has the property that A is isomorphic to the dual of A as left or equivalently as right A modules. And if we put a stronger condition on this, that of A being isomorphic to the dual of A as I bimodules, we will obtain the notion of symmetric algebra. So a general problem that can be formulated in a non-commutative algebra is whether a certain ring property transfers from an algebra on which a Hopf algebra acts or coacts to the subalgebra of invariants or co-invariants. And of special interest is the situation where the coaction produces a Galois extension. Okay, and from this general problem arises in a natural way our question that I posed earlier, and that I will repeat it. If A is a strongly G-graded algebra where G is a group with neutral element E and A is Frobenius or symmetric, does it follow that the subalgebra of the homogeneous component of degree E is Frobenius or symmetric? We have an interesting way of reformulating this question for the Frobenius property. In this sense, we look at Frobenius algebras in the monoidal category of G-graded vector spaces. Here, the Frobenius algebra in this monoidal category are called graded Frobenius algebras. And I recall also the definition of a graded Frobenius algebra that says that a graded algebra A is graded Frobenius if and only if A is isomorphic to the dual of A as graded left A modules or equivalently as graded right A modules. Okay, so we have in general that if A is graded Frobenius, it follows that A is a Frobenius algebra. However, the converse does not hold. And now, for reformulating our question, we will use a result from a previous work of ours of Călescu, Năstăsescu, and Năstăsescu that says that in the case that A is strongly graded, then A is graded Frobenius if and only if the homogeneous component of degree E is Frobenius. And using this result, we can reformulate this question using graded Frobenius algebras. So we'll have the following reformulation. So if A is a strongly graded algebra, which is Frobenius, does it follow, thus is necessarily graded Frobenius? So we try to do the same thing for the symmetric property, but we'll see that this does not work. So it works only for the Frobenius property. So I recall the definition of graded symmetric algebra. So A is graded symmetric if A is isomorphic to the dual of A as graded A bimodules. And we have the result that's in a previous paper that says that if A is strongly graded, that the homogeneous component of degree E is symmetric whenever A is graded symmetric. However, the converse is not true. So we do not have a result similar to this one for the symmetric property. So we cannot reformulate this question for the symmetric property as we did it for the Frobenius property. However, also this question for the symmetric property is of interest. The answer. Sorry?
What does the adjective strongly in front of graded mean?
Strongly graded, so it's when you have AG times AH, when you have the equality. Okay. Okay. Now we consider A to be a strongly graded finite dimensional algebra. If A is Frobenius, then it is left and right self-injective, and then the homogeneous component of degree E is left and self-injective. This means that the homogeneous component of degree E is a quasi-Frobenius algebra. So a possible answer of this question in negative is should be built on an a quasi-Frobenius algebra which is not Frobenius. Now we recall Date's theorem that says that each homogeneous component of the strongly graded algebra A is an invertible AE bimodule. So using Date's theorem, we can connect question 1 with the Picard group. So all these observations above suggest a study of the Picard group of the homogeneous component of degree E. In the second part, we'll consider R to be a finite dimensional quasi-Frobenius algebra. And we will look at invertible bimodules over this quasi-Frobenius algebra. And of central interest is the linear dual R star of the regular bimodule R. And we will show, in fact, that I will tell later that that in this case, this linear dual is an invertible R bimodule. But I will start by recalling the definition of quasi-Frobenius algebra that says that if we have a finite dimensional algebra, we recall that R is called quasi-Frobenius if its injective as left or equivalently as right R module. And afterwards, we give a characterization of quasi-Frobenius algebra that can be found in the book of Lamb, and that says that if R is quasi-Frobenius if and only if the left R modules R and the dual of R have the same distinct indecomposable components, possibly occurring with different multiplicity.
Which book is this?
Hmm?
Which book?
Yes, it's the book of Lamb, that lecture notes. Yeah, Lamb. Okay, so we have that in general Frobenius algebra is a quasi-Frobenius algebra. And now, if we have that R is a finite dimensional algebra, then the linear dual of R is an invertible R bimodule if and only if R is quasi-Frobenius algebra. And we will get also the result that in the case that R is Frobenius algebra, we'll have that the linear dual of R is isomorphic to the R bimodule R with the right action modified by the automorphism nu. Moreover, we will show that this nu is the Nakayama automorphism of R associated with a Frobenius form, and that the order of the class of R of the dual of R in Picard of R is equal to the order of the class of nu in the group of outer automorphism of R. And now we want to see the connection that exists between the Picard group of R and the Picard group of S, where R is a finite dimensional quasi-Frobenius algebra, and S is its basic algebra. And for this, we need some Morita theory. So let R and S be two Morita equivalent K algebra, and let be this a strict Morita context connecting the K algebras R and S. We have that P and Q are the bimodules, the RS bimodule and the SR bimodule. F is an isomorphism of R bimodules, G is an isomorphism of S bimodules, and we will denote by phi to be this bracket and by G the other bracket, and we'll have these relations. As in a paper of Takeuchi, a collinear monoidal equivalence F is induced between the monoidal category of R bimodules and S bimodules with a quasi-inverse given by this G. And now from this we will obtain that the mapping of the class of M that goes to the class of M is an isomorphism between the groups of Picard of R and Picard of S. And more of that, we have that the order of the class of M in Picard of R equals to the order of the class of Fm in Picard of S. And now if we will suppose more of that to take this R to be not only K algebras, but finite dimensional K algebras and Morita equivalent, and the FB, the monoidal equivalence as I described earlier. And we will get the following result, that there exists an isomorphism of S bimodules between F of the dual of R and the dual of S. And we, in particular, will get that the order of the class of the dual of R in Picard of R equals to the order of the class of dual of S in Picard of S. And okay, so I have to mention that this proposition, we will do it directly by using the tensor home adjunction, the duality property applied to objects that are enriched to the bimodule, and also some Morita theory. But I have to mention that the first proof that was suggested by one of the referees of this paper that also suggested this result to us to help us to do other things, and suggested also the proof, and they suggested to prove by using basic results from Nakayama functors. Okay. And finally, we will give the both proofs of this. And now if we consider R a finite dimensional quasi-Frobenius algebra and we consider S to be its basic algebra, then if we consider a complete system of orthogonal primitive idempotents, and if we take a system, if we take E to be a system of representatives of the so we will build it as in the book of Skowronski and Yamagata, and there it follows that this S is Frobenius and Morita equivalent to R. And we will have this following result from all of this, that if R is a finite dimensional quasi-Frobenius algebra and S is a basic algebra of R, then the Picard of R is isomorphic to the Picard of S, and the order of the class of dual of R in Picard of R equals to the order of the class of the Nakayama automorphism of S. Okay. And now in the fourth part, we will consider this calligraphic of R to be a 9-dimensional quasi-Frobenius algebra, which is not Frobenius, and we will study its structure and want to determine its Picard group. And this algebra was introduced by Nakayama in his work on Frobenius algebra, and appears also in a matrix representation in the book of Lem, but we will use here another representation that we gave in a previous paper of ours on a class of a quasi-Frobenius algebra. So we use this last presentation. I will describe a little bit this algebra. So let this calligraphic of R be this algebra with this basis given by E, x1, x2, y1, and y2, and Fej with Ej from 1 to 2 with the following relations, and any other two products being 0. And we will consider V1 to be generated in the following way: V1, V1 prime, and V1, 2. And we will get that this algebra is a decomposition of the indecomposable left R modules V1, V1 prime, and V2. And we will also see that V1 is isomorphic to V1 prime, but is not isomorphic to V2. On the other hand, if we take U1, U2, and U2 prime in the following way, we'll obtain that this calligraphic of R can be written as a decomposition of the following indecomposable right R modules. And we will also see that U2 is not isomorphic to U2 prime, is isomorphic to U2 prime, but is not isomorphic to U1. And now we will look to the linear dual of R that has the R bimodule structure induced of that of R. And we will denote by these partial arrows to be the left action and the right action. And afterwards, we will compute all these left actions and right actions on the basis. And using this computation that we do, we will get the following result, that the dual of U1 is isomorphic to V1, and the dual of U2 is isomorphic to V2 as left R modules. And consequently, from here, we will obtain that the dual of V1 is isomorphic to U1, and the dual of V2 is isomorphic to U2 as right R modules. And also, we'll obtain the description of this of this dual of this R star to be the direct sum between V1 and the square of V2 as left R modules, and in this way as right R modules. We also obtain that the dimension of this tensor product between Ui and Vj is 1. I have to mention that we did this first computational to obtain this by doing computation, but afterwards also one of the referees suggested us to do it in another way. So by using the tensor home adjunction also by using this previous lemma, and also by using a result from the book of Lorentz. Okay. First, in the first, so how we did it first? We did it first doing this, computing this dimension, and afterwards this result. But afterwards, we have it in another order. And now we will consider this basic algebra for this case of this quasi-Frobenius algebra, calligraphic of R, to be ERE, where E in this case is the sum between E and F11. And doing the computation, we'll get that this basic algebra is generated by E, F11, X1, and Y1. And we will get that the order of the class of the Nakayama automorphism of S in the group of outer automorphism of S is 2. And now we will, using this proposition, and also another result that I mentioned earlier, that the order of the class of the dual of R in Picard of R equals the order of the class of dual of S in Picard of S, we will obtain the fact that the order of the class of the dual of R in Picard of R is 2. Thus, we will have an isomorphism phi for this from this tensor product to R. I also have to mention that we can obtain this isomorphism directly by computations, and to see it, how it is. Okay, and now we are looking at invertible bimodules, and we want to obtain the Picard group of this algebra. So we will get the following results, that if P is an invertible bimodule, then P is isomorphic either to the direct sum between V1 and the square of V2, or to the direct sum between the square of V1 or V2 as left R modules. And we will show that any invertible R bimodule is isomorphic to either this R bimodule with the right action modified by the automorphism of alpha, or to this dual of R with the right action modified by the automorphism of alpha. And as a consequence, we'll get that the Picard group of R is the direct product between the group of outer automorphism of R and the cyclic group C2. Okay, and in the following part, we want to compute the automorphism of this quasi-Frobenius algebra, which is not Frobenius. And now here we will use the presentation that I said that appeared in one of our papers on a class of a quasi-Frobenius algebra. So we can see that this algebra is isomorphic to the Morita ring, connecting the rings to the Morita context, connecting to the rings K and the 2 by 2 matrix with elements in K, and with the following bimodules, X and Y, and with action given by the matrix multiplication and both Morita maps being 0. I have to say that this Morita map and the 3 by 3 matrix with elements in K are the same as vector spaces, but have different multiplications. So the multiplication here in the Morita ring is given differently by collapsing the elements on the diagonal blocks. So we'll have different multiplication, and we can identify this calligraphic of R, this algebra, to be this Morita ring. And now this multiplicative group K star direct product with GL2K acts on this additive group in the following way. So we can form this semi-direct product between this additive group and this multiplicative group. And we will get that the automorphism of R is isomorphic with this semi-direct product as isomorphism of groups, and we'll get also that the group of outer automorphism of R is isomorphic to this multiplicative group of K star. Okay, and I also have to mention that if we do this, if we compute this group of outer automorphisms by the 3x3 matrix with elements in K, we will get that this is trivial. But for this, it's not trivial. And here is the reason, because the multiplication are given in a different way. Okay? And in the last part, we will build a general construction of semi-trivial extension, and we will use this semi-trivial extension to answer in negative to our question. And first I will give the construction of semi-trivial extension. So we consider R to be a finite dimensional algebra, and this R star to be its linear dual, and this R star has the usual R bimodule structure induced from that of R. And the action are as before denoted by these arrows. And we consider Psi given in the following way to be a morphism of R bimodules. And we will denote this Psi in the following way. We say that on Psi we have associativity if we have the following relation. And in this case we have a Morita context connecting the rings R and R with both bimodules, the dual of R, and both Morita maps equaling Psi. And from Morita theory we'll get that if Psi is associative and surjective, then it results in isomorphism of R bimodules. And now if we consider this Psi to be an associative morphism, we will consider this semi-trivial extension in the following way. By the Cartesian product with the usual addition and the multiplication defined in the following way. We see that in fact this semi-trivial extension has an algebra structure with the identity given by 1 and 0. And this construction was did by Palmer in one of his paper. And we also see that that an algebra is a C2 graded algebra with the gradings given in the following way. And now we have that this semi-trivial extension algebra is graded algebra if and only if C is surjective. And from what I said earlier, if and only if this Psi is an isomorphism. So we will have that this semi-trivial extension, so this algebra is strongly graded if and only if this Psi is an isomorphism of R bimodules. And now we will show that in the case that R is a finite dimensional algebra and Psi is an associative morphism of R bimodules, then we'll get that this algebra is also a symmetric algebra. So we will prove that it is in fact a symmetric algebra. And now I will give some examples. So if we take this Psi to be 0, we will obtain the trivial extension and the multiplicity given in the following way. And this is just the renowned example of Tachikawa of a symmetric algebra constructed from R. And afterwards I will give also another example when we consider R to be a symmetric finite dimensional algebra. Okay? And now we will return to our example of calligraphic of R, where this is a nine-dimensional quasi-Frobenius algebra, which is not Frobenius. And we saw that in this case, this phi from this tensor product to R is an isomorphism of R bimodules we proved earlier, and we will denote this C to be this pair. And we will show that in this case of this particular algebra, we have associativity, so the associativity work. So for this, because we have associativity, we can construct this semi-trivial extension in this particular case. And this algebra will answer our question in negative. So more precisely, we will take this algebra where in this particular case of where this calligraphic of R is a quasi-Frobenius algebra which is not Frobenius, and with the grading given by the homogeneous component of degree E and the homogeneous component of degree C given in the following way. And because, as we saw, that this phi is isomorphic, it is clear that A is strongly graded. And also we have proved in the general case, not on this specific case, but on the general case, that we also have symmetry when we have that this phi is associative. So it follows that is also symmetric. However, the homogeneous component of degree E that is not even Frobenius, it's only quasi-Frobenius. So this is that.
Thank you. I hope that everybody is on the picture. Then you get your evidence that you were attending a conference, not doing tourism. Now let us start with next talk by Daniel Bulako from Bucharest University, and he's going to talk about double B product and quasi-quantum groups. Okay.
As you wish. I can start or we can wait?
I think everybody's here, maybe we can start. Huh? Yeah? Yeah? Okay, yes, go ahead.
Okay. Thank you for the extra 3 minutes.
He was negotiating for 10 minutes. I said, no way.
No way. But at least I have 3, and this is good. Okay, thank you very much, and also many thanks to the organizers, especially to the organizers, the local ones, the ones from Turin and Ferrara, and other places from Italy. I know that they did a hard job to have this conference, and I'm very pleased to be here, and also very pleased to give this talk, which is joint work with Daniel Popescu and Blas Torresilias from University of Almeria. So why double biproduct quasi-quantum groups? Because our ultimate goal is to define the quasi-Hopf analog of UQ of G. And we try to do it in several ways, but it seems that without categorical machinery behind, it's impossible to achieve this goal. And what we realize, at least in the braided case, or of course is not our situation, because quasi-Hopf is not a braided Hopf algebra, but serve as a model. We observe that we can introduce at least the double biproduct quasi-quantum groups by using the categorical machinery. And also, we can produce deformations of them by two co-cycles. And by achieving these two goals is possible, and at the end was possible indeed to define the quasi-Hopf analog for UQ of G. Was not easy, it's a lot of work behind, but this is part of the work you done for defining UQ of G. And now some history about the byproduct quasi-Hopf algebras, and then how we can construct the double byproduct, and what is a two co-cycle deformation in our setting, and if it will be time, some concrete examples. If not, then Blas will continue and will present you the relevant ones. We took the advantage of the monoidal categories to avoid very complicated computations, which came because of the apparition of the reassociator of a quasi-Hopf algebra. So all the structures we obtain them by using or by specializing some formulas coming from the categorical context. So we had not to perform any kind of computation. Everything is for free. So the starting point was an article of Bespalov and Drabant combined with the Majid's paper about double byproduct construction. There is a connection between the two. In the case of Majid, everything was done, let's say, by hand. So relations and then computations and I don't know, Hopf algebra structure, the deformation, and so on. But by following the Bespalov and Drabant construction, we saw that the Majid construction has a categorical flavor. And this categorical flavor was used even in this quasi-Hopf case, because we have to deal with two categories that are braided, are actually braided equivalent, namely the category in four corners is the category of two-sided, two co-sided Hopf modules over a quasi-Hopf algebra this time. This is braided with tensor product over H. And it's in the Hopf case is a well-known result proved by Peter Schauenburg many years ago that this category is braided equivalent to the category of Etter-Dinfer modules. Actually, the structure theorem for Hopf modules can be extended in a way that allows us to find the braided equivalence. Now we have structure theorems in the category of four corners. There are two versions, the left and right one, and by using them we can construct the double, not the double, the byproducts, the left and right byproducts. And why? Because the Hopf algebras in this category of four corners can be characterized as quasi-Hopf algebras with projections or as byproduct quasi-Hopf algebras. So any Hopf algebra in the category of four corners is completely determined by a braided Hopf algebra in the category of Etter-Dinfer modules over H. And now because of the left version of the structure theorem, B can be in the category of right Etter-Dinfer modules over H, or in the category of left Etter-Dinfer modules over H if you are working with the left version of the structure theorem. So we have actually two Hopf algebras inside of this category in four corners. At the beginning, we denoted them by C tensor H and H tensor B. And if the two Hopf algebras satisfy a natural compatibility relation. In general, if the category is symmetric, we don't need the compatibility relation. I mean, when you have the tensor product algebra and the tensor product coalgebra, we can combine the two structures to obtain the tensor product Hopf algebra of the two objects, but provided that the category is symmetric. If the category is not symmetric, then you have to at least to ask the braiding of the category to be symmetric at the level of the two objects that we consider. So in our case, the two objects are C tensor H and H tensor B. So once this symmetry is satisfied, then we can take the tensor product Hopf algebra of 2, but in this category when the tensor product is over H, and in this way we have a new Hopf algebra in this category, which we know that is a byproduct. So
sorry, you cannot use a light because cannot be
okay.
broadcasted.
Okay.
No, you can use the mouse.
Ah, the mouse. Okay, I don't use the pointer. Okay, thank you. So we have this new Hopf algebra coming from the two, which we denoted by C cross H cross B and called the double biproduct quasi-Hopf algebra of A, C, and B. And the quasi-Hopf algebra structure we obtain is for free because it's coming from the tensor product of two Hopf algebras in a given braided category. Just to explain a little bit the structure and also the terminology that we used, I recall some facts about the structures of algebras and coalgebras and bialgebras and so on in the category of two-sided, two-cosidal H modules. So first of all, the algebras inside of this category are left smash products. The coalgebras are what we call the smash product coalgebras. So the smash product algebras are defined by algebras in the category of Dieter-Greenfeld modules. Actually, we need only to be an algebra in the category of left edge modules in order to perform the smash product construction. But to have it as an object in the category, the algebra has to stay in the old category, in the category of Dieter-Greenfeld modules. Good, and something similar for C, when this enough to have this C just as an H module coalgebra. So here is the definition of the co-multiplication of C cross H of smash product coalgebras. As you see, the formulas in general are very complicated due to the multiple apparitions of the reassociator of the quasi-Hopf algebra H. But as I told you, we don't have to compute anything, so everything is coming for free. And now is the old structure of this guy. So the algebra structure is the smash, the coalgebra is the smash coalgebra, and the reassociator is produced by the reassociator of H, and here is the formula for the antipode. So this is the left version. We have also the right version when we work with if you like, with the right structure theorem inside of this category. Again, complicated formulas. Here we have also some special elements that are defined in a quasi-Hopf algebra. Alpha and beta are coming together with the definition of an antipode for quasi-Hopf algebra. And then is a connection between the two constructions, so a connection between the left and right byproducts. Actually, they are isomorphic. It doesn't matter with what version we work as quasi-Hopf algebras, they are isomorphic. And why so? Because in general, we have results coming from the center construction, saying that the left and right Jeter-Drinfeld module categories are isomorphic as monoidal categories, and even more as braided categories, but for one of them the braiding is not the one coming from the center construction, is coming by taking the mirror reverse version of the braiding. It's like in the quasi-triangular case, when once you have an R matrix, a second matrix is R1 to the minus 1. So it's the twisted matrix, and then we take the inverse. Good, but we want to be not from one of them to the mirror version of the other one. We want to be from left to right, and we can do this with the help of the braiding of the category. And to make a long story short, we have a braided monoidal functor between the category of left and right Jeter-Drinfeld modules. And so we can associate to be a braided bialgebra in the right category, a B bar, another braided Hopf algebra, but now in the left version of the category of Jeter-Drinfeld modules. And when you transport the structure, we get something like this. You know, is the action is given by considering the inverse of the antipode, and for the coaction we need the Drinfeld twist. Is this element that controls the fact that the antipode is kind of anti-coalgebra morphism. And what is with a big dot there is a new multiplication on B, and for the co-multiplication is something more complicated. But again, everything is coming for free by using the braided equivalence between the two categories. Okay, and then in the situation when you are working with algebras or co-algebras in one of the Jeter-Drinfeld module categories, we have this isomorphism between the left and right version of the smash, and something similar for the co-algebra setting. And what is remarkable is the fact that in both cases the isomorphism is the same. It's induced by this map, and here is its inverse. And also this isomorphism is an isomorphism at the level of quasi-Hopf algebras. Good. And now is the compatibility relation that I mentioned before. So we need it in order to produce the tensor product Hopf algebra structure in a category that is not necessarily symmetric. So it's just braided. So once this condition is satisfied, then we can put together the left and right. And because everything is under the tensor product over H, we have this object with H in the middle. So it's CHB. But what can be proved is the fact that this double byproduct is actually a left or right byproduct. We saw that we can move from left to the right with the help of this B bar. And why is so? Because when you have B coming from the right, we move all the structure to the left. So now we have C and B bars staying in the same category, the category of left Jeter-Drinfeld modules. And because that compatibility relation is satisfied, we can produce the braided bialgebra inside of this category. And to emphasize somehow this construction, we put a tilde on the tensor product. So this is the tensor product of the Hopf algebras C and B bar in the category of Jeter-Drinfeld modules. And then here is the structure of the double byproduct. You see again some complicated structures. So the multiplication was discovered in 2006, so many years ago. At that time we call it a double smash product. We never thought that it can be let's say the algebra support for this construction. So okay, so we discover it again, and now the co-multiplication is written in two ways, just to see that both left and right byproducts are included in this double byproduct. You see, so here is, let's say, the left version, followed by something, and here is the right version, followed by something. So this double byproduct contains both left and right usual byproducts. Okay, and now this is the formula for the antipode. Imagine how work must be done in order to prove that this is an antipode. So I think it's almost impossible, but I told you everything is coming for free, so it's nothing to prove here. Okay. But what is important for us, we see later on why, is to identify this double byproduct with let's say, the left version of the byproduct. And we can do this. We have an isomorphism here, and the inverse is not written here, but we have an explicit formula for the inverse too. Good. So it's important to have this double byproduct characterized as a simple byproduct, because the next step is to deform by two cocycles. And at a certain point, we had no idea how to define a two cocycle for quasi-Hopf. When you deform by a two cocycle, at least in the Hopf case, we have to deform the multiplication, and we have to stay in the associativity, in an associative setting. So, what condition to put on the two cocycles? With structures like this is quite impossible to discover the definition. But once again, we found a categorical way to do it. I explained this in a previous conference. We used the duoidal categories, and the bimono is there in order to define the two cocycles for a quasi-Hopf, and then to see that the deformation by two cocycles is again a quasi-Hopf. So if we work in a braided category, then everything is clear. We have a definition for a two cocycle that generalizes, let's say, the classical one, the one that we have in the case when C is the category of vector spaces. And also, it makes sense to speak about the invertibility of the two cocycle, because we have a convolution algebra here. So the invertibility is with respect to the convolution product. And once you have an invertible two cocycle, and theta bar is the inverse, then we have a new multiplication on the bialgebra or Hopf algebra A, and with respect to this new multiplication, we have a new bialgebra, braided bialgebra, or a new braided Hopf algebra. So the new antipode is defined in this way. But we can say something more, because we have the braided equivalence between the category in four corners and the category of Dieter-Drinfeld modules. And let's say the meaning of this theorem is to apply it in the case when C and D are those two categories. So for short, once you have a braided equivalence between the two braided, of course, categories, then we can transport the two cocycles from one category to another. And moreover, we have a connection between the, let's say, deformed objects. So here is A deformed by T. And then we apply the functor. Is the same like applying the functor and then the two cocycle, but now in the other category. So this is behaving well with the byproducts, but it's not the case that we want, because the quasi-quantum groups, they say, or the quantum groups in general, are not Hopf algebras with projections, are Hopf algebras with weak projections. and then are not byproducts, are something weaker. And this is why we have to do something different. And here is what we did. So the first thing is the fact that we can define two cocycles for a quasi-Hopf only if we work over a sub-object, a sub-quasi-Hopf algebra that, let's say, contains the components of the reassociator. So, for instance, when you take, so for the Hopf case is not the case because we don't have a reassociator. There is trivial. So the sub-algebra is K itself. But here we need this K. In the case of a byproduct, so the byproduct is denoted by K, is R cross H, then H is the sub-object that we need because the reassociator for K is coming from the reassociator of H. And then the two cycle has the same definition like in the Hopf case. The difference is made by the fact that we have to work with tensor product over H instead to work with tensor product over K. And then what can be seen is the fact that the two cocycles in this sense are given by the almost two cocycles for the bi-algebra R in the category of Dieter-Drinfeld modules. So this is precisely the two cocycle condition in the category of Dieter-Drinfeld modules over H, but with one exception, namely this V, this H-linear morphism is not H-collinear. Because if it's H-collinear, then let's say we are in the ideal case when you get again a byproduct, and this is not our, should be not our case, because I explain you we are working in a weaker context. But when you have to find two cocycles for a byproduct, actually we have to work, to look at almost two cocycles for, let's say, the diagram of R. Good. Now, let's come back to the double byproduct. So the double byproduct a double byproduct can be identified to the simple one. And now, by looking at the Hopf case, we are interested in finding those two cocycles that have a particular form, namely are defined by that capital sigma. So we act with the co-unit of C on the left, co-unit of B on the right, and put a suitable linear map capital sigma from B bar tensor tilde C to K. And now to make the required relation for sigma more transparent, we replace B bar by A, because on the next slide you'll see how they will look when you put back B bar. So what we have here is nothing but a skew pairing between A and C, but in the category of Dieter-Drinfeld modules. So if you forget about the reassociator, so we delete all the X, Y, and so on, what you get is precisely the definition of a skew pairing, but it's again almost a skew pairing because it's not H-collinear. So we don't ask V to be H-collinear, so this sigma has not to be H-collinear. So when you have it in terms of B, you see we get something that it's almost impossible to achieve. But it's not the case, because what can be proved is the fact that due to this isomorphism between the double byproduct and the simple byproduct, we have a one-to-one correspondence between those capital sigma satisfying those strange relations and linear maps sigma from B tensor C to K satisfying the same relations like in the Hopf case. So are quite simple relations. So instead to look at sigma, we look at the small sigma, and actually the small sigma has to be defined only on the, let's say, algebra generators of B and C, because you see we can't extend the sigma to the all B tensor C by using these two relations. Good. So now some examples. 5 minutes left, which is good. Instead of working with left and right braided Hopf algebras, we prefer to work with braided Hopf algebras in the same category, to make the simple byproduct and maybe to move through the isomorphism, let's say, to the double byproduct quasi-Hopf algebra. So this is why for these quasi-Hopf algebras introduced by Ettinghoff and Gelacki in 2004, we have projections for them. And if we have projections, then we have braided Hopf algebras associated to them. The projections are onto the two-dimensional, if I am not wrong, quasi-Hopf algebra KC2. This means is the group algebra of C2, is the Hopf group algebra of C2, but now seen as a quasi-Hopf algebra with a non-trivial reassociator. So if we look at the three cocycles in the group sense, there is only one non-trivial cocycle when the characteristic of the field is different from 2. But we don't need the cocycles to be maps, we need to be elements. And then we have to use the duality between KC2 in this case and KC2 star as Hopf algebras, and by using some canonical isomorphism we get this reassociator, non-trivial reassociator for KC2. And you have an antipode and the distinguished elements alpha and beta. Alpha is G, the generator of the group, and beta is 1. And then we have two braided Hopf algebras, because I told you there are quasi-Hopf algebras with projections. And when we compute, here is a general, let's say, way, is a machinery that allows us to find the braided structures. We get these two braided Hopf algebras, R plus and minus over H2. Here are all the structures, and then we characterize the multiplication and the co-multiplication for the two. We can put the structures together. So plus is for the R plus, of course, minus for R minus. So, and I is a primitive root of unity of order 4 in the field. And then is the antipode. Good. And when you take C was in the left, and B bar now is directly R minus. Of course, it's no way to go to the right to come back to the left again. So we do it again. We do it directly in the left category of Yetter-Drinfeld modules. Then one can see that the symmetry of the braiding is respected for the two objects. So we can take the braided Hopf algebra in H2 over the Yetter-Drinfeld, and in this way we get a 32-dimensional quasi-Hopf algebra, which is actually a double byproduct quasi-Hopf algebra. So it will contain the two byproducts, which in this case are both of the dimension 8, are the H plus minus 8 initial, let's say, quasi-Hopf algebras. And now if we want to deform it by something, then the sigma can be parameterized by a scalar in K, and we can apply the machinery and get the deformation of the two cocycle. And another example is based on the work with Matteo Misurati. We computed some braided Hopf algebras of dimension 2 in the category of Yetter-Drinfeld modulus over KC4, but with this special reassociator. And if you repeat the things for the two guys we have here, we get another quasi-quantum group of dimension. Thank you.
Questions? Comments? Yes? Go.
was a lot of formulas. I didn't follow every single equation, but in your double byproduct, there is the single byproducts are so there is no middle term. There is no structure element that goes from C and B, tensor B to H, or is there? So it's just it's in a sense a self-dual construction. Do I understand this correctly? The co-algebra structure and the algebra structure are strictly dual, or is it not self-dual?
No. So we have something in the middle for the double byproduct construction. So we C, H, B. This is the order.
Yeah.
But it can be always identified with a usual byproduct by taking C tensor product with B bar. So it's what we get when you move B from the right to the left.
Can we maybe look at the formula again, at the multiplication formula?
The multiplication formula for?
The double byproduct. First.
Oh, okay. So is that double smash product?
Yes, this one.
Okay, so I have to move a bit back. Okay, we are close.
This one.
Is this one, exactly.
Yeah, and so there is, if you forget about the associators,
Yes.
which are the x's, the y, and the y's, right? These are the s and the z's are associators, yeah?
Yes,
Then you,
but we have H in the middle.
Yeah, but you have there is no map in the part that goes from C tensor B to H.
To go from? From C tensor H to?
From C tensor B to H. There's no, it's just a kind of multiple, it's just the two formulas for the byproduct combined. I think I see it now, yeah.
Yeah. Is the smash, the left, the right, and just to combine the two, we need an extra copy of the reassociator.
Yeah.
See? So if you look at the y's, it's for the left. If you look at the z's, then it's for the right. But we need also the x's.
But if there would be no associator and only then the C and the B, they would commute.
Yes, then this is something isomorphic with this guy when you make the tensor product of them with H. So if you take the tensor product of the algebras, yeah, C and B bar, is again an algebra. Make the smash product, and it's isomorphic with this guy.
Yeah. Okay. So, but in the C tensor B bar, C and B commute.
You mean to commute in the? I don't know if they commute. Especially C and B bar, I am afraid that they don't commute.
Okay, we'll discuss it later. Maybe.
Yeah. The quasi-quantum groups appear as examples. So you expect to have an R matrix maybe, no, or something.
It's in the title,
Yes, and this will be better explained by Blas, because there are many other applications of these constructions, and maybe the applications that we'll see next will explain the terminology, why we use quasi-quantum groups. Okay.
Thank you. Let's take. Just technical break.
Okay, so it's in good hands now.
We have a last talk of this afternoon, and it's by Blas Tordesillas from University of Almeria, and the title is the quasi-Hopf analog of the Drifel-Jimbo quantum groups. Please.
Okay, thank you very much, first of all, for the organizer to first organize the meeting, and second, invite me to the meeting. Okay, and then I would say maybe will be a quasi-analog of the infragimbal quantum group. Okay, the idea is to use the machinery that Daniel explained to construct something similar, analog to the quantum group that appear here. Okay, then we introduce what we call a quasi-free Jeter-Drinfeld. Well, first H would be a quasi-Hopf algebra with bijective antipode, and then we introduce what we call a left Jeter-Drinfeld datum as a triple of a set of elements, EI and H, and some character, Chi, and R, an element in H tensor H. Then we ask to satisfy, this is familiar for you, satisfy this condition of the R over condition or R, okay? You can recognize that this is okay, the R matrix. In fact, the condition we impose is part of the definition of the R matrix for H, and only use part of them, not the complete one. One is omitted because, okay, if you prefer, you can think only in the R matrix, a quasi-triangular. But I think in one of our applications, it's necessary to do it more general. And then this is why we introduce the semi-quasi-triangular quasi-Hopf. Okay, well, we will use also that you have a R matrix, semi-R matrix is enough. Semi-R matrix, then you can find the formula works, the usual formula for the inverse of R as in the quasi-triangular case. Okay. Now we want to observe that given a Jeter-Drinfeld structure over one-dimensional vector space, is just to give a pair of chi and one element A or R, A maybe, don't compute with is K maybe, consisting the character and element in H, satisfying this the condition you can read there. Okay, and then this is that you have a semi-matrix, any character determine the Jeter-Drinfeld module over if is dimensional vector space. Okay, then we are interested in only one-dimensional, something like the Picard group, if you like. And then this is a set of pair, we call this a set of pair of all these pair of elements satisfying these three conditions. Okay, then the properties you have for this pair is that you can define a composition law into two pair, the element, the formula for the element. You have to little more complicated, but kappa, the character k, chi and 1 and k2 is just a convolution. Whereas the properties you define a group. The operation is associative. You can show this is associative. 1 epsilon is a neutral element, and you can find explicitly by these formulas explicitly what is the inverse of any subpair. Okay, here we use Daniel said before the Drinfeld twist, and in the inverse that control the inverse here. We can compute the inverse here then. And then we have defined a commutative group using this pair. And now we are, this is the first step we need, first part of the construction. The second part we need a family of elements as before, and a family of character. And we are going to define what we call a left quasi-word in the alphabet E. It's a sequence of elements of words, but we keep the parentheses because we are going to do something non-associative, and then we associate always in this way. We write from E1 to EM, putting the parentheses exactly in this way. Okay, and we also include the empty word. Okay. Okay, here, okay, this is what I said, no? The last observation is that because it's not associative, but we are going to control the associativity using the reassociator of the quasi-Hopf algebra. Then we denote the quasi-free K-algebra over this set E, and we denote this way. Maybe I can show. This is we denote on the left as a vector space of all the left quasi-world in E and the empty work, and the multiplication is given just by concatenation. Okay, but then what do you have this? You have to put in the and this you can see that you obtain. You can move the parentheses and finally obtain one scalar and a word in this a word defined in this way. Okay, putting all the parentheses in the appropriate order, moving all the parentheses from one side to the other. What is the rule? The rule is that you have the associativity is controlled, but you have this on the left, the parentheses on the left. Then you take the reassociator and take the image of the reassociator as the scalar, and then you move the parentheses. Okay. This is extended, for any two quasi-words. You do all the same every time the same, and then you see that finally you will obtain some product of the character which appear here. Okay. We did denote this k of omega of the double view of some word is the multiplication in this order of the character, convolution of the character. Okay, and the unit of this will be the empty word. Now I put one example to see how this how you can move exactly the parentheses when you try to multiply, for instance, these two. Well, but because the problem is this is well defined. It depends on the order you move the parentheses, because you can move the parentheses in many different ways. And the problem is if you move in the parentheses in any way, you always obtain the same element. And then here is one example of how we move the parentheses here. Then we multiply, associate the two first, and then you have to apply kappa of the first one, kappa 1 of x for the reassociator. The second word is E2, kappa E2, E3, x2, and then the third one is kappa E prime is applied to x3, and then you apply that you have this new associations. And now we associate these two to obtain, associate E3 with the rest, and E2 in the front, and we keep E1, and then you see which appear the other copy of the reassociator in this order, kappa E2, E3, and then the same E3, and finally you, okay, no, this is okay. This is already a word in our canonical form because all the parentheses appear from the right, and this is okay. What they made here is just, I put kappa E1, the kappa E2, you can put together kappa E2 of x2 with kappa 2 y1, and the same for kappa 3, and then we finally obtain this formula for the complete reassociation of this one. If you do in the other way, you make another way of make the association. For example, here we make the association inside, no? E1, 2, E3, and then we use just the inverse. This has to be the inverse of the reassociator, kappa E1, E2, E3, and this one. And now we associate E3 here, and then we keep E1, E2, and so on, using the same way. We obtain apparently a different formula. This one is one formula, and the other one which appear here. But this is, you recognize that this is exactly the three-cycle condition for the reassociator. Okay? And then this is controlled really by the properties of the reassociator. And then with this, well, this is not a complete proof, it's the first step. Later you have to really obtain a proof for the general way of moving or associate the parentheses and show that this is exactly, you always have the same element. Okay. Now we are going to extend or put Jeter-Drinfeld structure over this object. We have construct, and for that we need an element in the Jeter-Drinfeld one. Say you need a structure of Jeter-Drinfeld over the element EI. You need ECI need to be this one, associated to this one, and then the Jeter-Drinfeld is the action is described here with the kappa of H E1, and the coaction is just the element tensor E1. Well, again, the difficult things here in this proposition, the difficult thing, okay, you have to extend this by, this is the formula for the E, then you have to extend the formula for the word, and this depends on how you associate the word, and then you have a little word. You have to word in order to show that this exactly is defining a structure of Jeter-Drinfeld structure over this quasi-free, left quasi-free algebra in general. No? Okay, this is a way we call free in some sense because this has this universal property, and this is you see you consider the inclusion map from E to KE, and A is in algebra in Jeter-Drinfeld, then each map satisfies these two conditions. For any map satisfy these two conditions, you can extend to an algebra morphism in Jeter-Drinfeld. In some sense, this is the freeness we are working here. For now, we want, of course, to get the quasi-Hopf algebra, then we need also a comultiplication. For the comultiplication, we need to introduce or recall, we are use the shuffle of with the node by S and S, and S, all the shuffle, NSM shuffle, okay? With this property, we know they are N over S, and also we will use the inversion of sigma that is well known, okay? And this is, and then with this notation, we can obtain a formula, complete formula for the description of the commultiplication over a word. Okay? The first one is over the element EI, say that these elements are primitive. And then for any quasi-word, this should be the formula over all the shuffle, and then this using the inversions to apply the kappa to the element, and then you split in two parts the word. Okay? Then we show that this is a coalgebra, and this gives you a structure of bialgebra over the Jeter-Drinfeld category. Okay, then we can state this as a theorem. You have a family of elements, a family of EI, and a family of kappa I say AI kappa I, and Jeter-Drinfeld 1. And then we take the quasi-free algebra, then it's a Breide-Hopf algebra and Jeter-Drinfeld. Okay? We have construct all the structure. The only need is just, I think I state all of them in the previous one. The only need is to say the formula for the antipode. And the antipode you can also define. This formula should be the antipode for this algebra, quasi-Hopf algebra. Okay. Now, we have a presentation for this algebra. This is, you take a quasi-Hopf algebra, family as before, and then we are defined now what is the byproduct associated to KE. Okay? KE has, we saw that this is a Hopf algebra in the Jeter-Drinfeld category, and then we can define the byproduct quasi-Hopf algebra associated to it. We'll call E, and we have exactly this presentation. It's an associative algebra as a unital, and it's generated by a family of elements, EI, and the element of H. satisfy this condition, A is I, is kappa I S1, EI S2, the co-multiplication of delta I and the co-unit, and determined by this formula. This is the formula of the, formula of the co-multiplication. You see here appear the reassociator, the two copies. This is X, I said that S, capital X is the reassociator, Xi, smaller x is the inverse. And also you have an explicit formula for the antipode, okay? I put over EI, then you extend by the anti-homomorphism in the algebra. Okay, in order to do the construction that Daniel said, this double byproduct, then you need also a right version of the quasi-free algebra, and this is defined in a similar way. Okay, you take the family of elements, now a family of character should be different character defined over H, and we take the vector space, one-dimensional vector space as Jeter-Drinfeld, defined by the element, and then we have here, we know it's defined by one element and the kappa I, and then this is the property of the element you have to introduce. Again, the family of all these elements, it gives you an abelian group, and you can define what would be quasi-word writing on the right, starting on the left, the parentheses, and you can obtain the similar result on the right of this structure. Okay? Now we need to perform, you remember, we need to perform the double byproduct, and then we need the compatibility between the two structures. In this case, the compatibility, you remember this is the equation for the compatibility. You specialize in our case, and then give you this property of kappa bar, and this is exactly what happens if and only if this is equal to 1. Kappa j r I, kappa I, b j is equal to 1. Okay? Okay, you have an R matrix, this is immediately satisfied, and you are safe. Okay? Okay, now is the description of the double byproduct. You can describe, in this case, the double byproduct that Daniel constructed in general for this construction. You assume that E and F are compatible in this sense. This is reduced to this in order to make the double byproduct. And we can describe this algebra. Okay? This is going to be a quasi-Hopf algebra, but as an algebra, it's a unital. It will be generated by the EI in Fj, okay, satisfying these two conditions written here, the three conditions written here. And the quasi-Hopf algebra structure is given by the delta EI of Fj, these formulas, and you can extend this from this EI to the generator, and you also have a explicit formula for the antipode over the generator, and you extend at the anti-morphism of algebras for all S. Okay. We said, also Daniel said that the double byproduct can be isomorphic to really a left or right byproduct, you remember. In this direction, we need to first obtain the F bar and move to the right to the left, F bar, the category of left Jeter-Drinfeld. And here is how you do this, following the formulas. In this case, it's not complicated. You define the action on the left using the inverse of the chi, of the character, okay? And this has to be extended to the whole one using the property of the H action, and the same you can define using the structure of the co-multiplication. And here is how you define the multiplication for these two, and the rest is the same structure of F. You modify only the multiplication. Okay? Then we move already, F has been moved to the left Jeter-Drinfeld, And now, with this, you remember the notation, we make the, in this space, we make an algebra, coalgebra inside the Jeter-Drinfeld category, what allows you to give obtain the associated byproduct. Okay, I'm going to give you only the formulas you find for the associated byproduct of this quasi-algebra. Is this the quasi-algebra you obtain tensor byproduct with H? Okay. Here you have the generator EI, Fj bar, and H, and here is the relation as an algebra, okay? And the formula of the commultiplication is defined here, and here is the formula for the, you see in this case we can explicitly define the formula for the generator, okay? Of course, it's complicated. You see that every time you need several copies of the reassociator. Okay. Okay. We want to also to make a quotient with the set relation. In our case, that in our case the set relation transform in this one with the property of the character. You recognize the usual. But here with applying the character to the formulas. And then you have these two, we define the quotient, these two new algebra, E prime, F prime will be the two quotient. And now we repeat to obtain the double byproduct of these two algebra. In fact, this has a similar description, I'm not going to say, it's a similar description of E tensor F, but adding the two set of set relation that I mentioned. Okay, but then we need, moreover, we need to take a two-cocycle deformation. Recall that this is the last step. Here, the two-cocycle can be defined just using a linear map satisfying these three conditions. Okay. And from here, we obtain the three-cocycle over the object, okay, defined by this formula. And this is exactly a two-cocycle over the double byproduct. Okay. For our case, for this particular case, we can define the sigma can be defined just in this formula, where these are constant elements. Okay. Then this deformation has also a quasi-algebra structure is the same, and the algebra structure change using this relation you find here. Okay, you can see appear kappa and appear also the R quasi-triangular structure. And the antipode, I don't write the formula for the antipode, but you can see from the other one. Okay, now we apply this for the case of classical case of the Cartan datum, and here I is finite. We have a usual description, and we know that it has a quasi-triangular structure defined in this way. The problem we have here is that we don't have in this free abelian group, we don't have three-cocycle, and then in order to introduce a three-cocycle and go to the quasi-Hopf world, we need to tensor with one quasi-triangular quasi-Hopf algebra HR. When you make the new big algebra, big quasi-Hopf algebra, then we have an R matrix here, and we can extend the character we start with. We can extend this character to the big algebra, the tensor algebra, and with this character, we can consider the quasi-free algebra EI over this new Jeter-Drinfeld category with the big algebras, also for this, and the deformation given by the same formula as before. And with this, we can obtain we can construct a quasi-Hopf algebra. What this is looking for. That we have here. These are the generator now is EI, FI, the dual basis, P mu and H. And here is the relation of the algebra you have. This one, you have to add this commutator for this algebra. And also, you have to add here the set relation. Okay? And this is how it looks like the set relation for our case. Okay? Finally, okay, this is a concrete example. You can think for the cyclic, I think that Daniel was considered here. Maybe I will go directly with something to the other example I find more important for us is the symplectic fermion quasi-Hopf algebra that appeared in a paper by Farsak and Goodenough and Runkel. And they construct this, well, motivated by physics, they construct this quasi-Hopf algebra. It's given by relation, generator relation. It's generated by one element K and two families of element F plus minus. Okay? So you can find the F and the G, the E and the F you like. Okay? This is the relation. You see this is anti-commute. This is the relation that with the not the commutator. This is with plus. This is not the commutator, and here igual is the other one. Anti-commute. These are two anti-commute. This is the relation between the positive and negative. Be aware that here you take, there is one here that gives you that fj squared is 0. Okay, E1 is one of the element, is the idempotent element. If this is K4, we are working the cyclic group, and this is one of the idempotent. And here all elements are dimension 2. All the element has order 2. The fi squared is 0, because in principle it's an algebra which contains the Clifford algebra and contains the stereo algebra also inside this algebra. Okay, this algebra you can see like the quasi-Hopf algebra, taking K. Okay, here I don't put the general case. I only put the odd case. It's more interesting for us. Because in the odd case, you have this commultiplication. This K become group-like, and this is the commultiplication for the Fj. Okay. In this case, we have the accretion of our reassociator. Okay, this is different for that. And what we can show is that you take the cyclic group, you take the psi2 reassociator, and you twist this reassociator, we can obtain exactly the reassociator that is given by the author in the paper. And then, because we want to find a quasi-triangular structure, and then we know how is the quasi-triangular structure for F2 or phi2, but we don't know the quasi-triangular structure for our further reassociator is used in this quasi-Hopf algebra. And then we have obtained the matrix. We can twist the usual matrix, the usual quasi-triangular structure, to obtain the quasi-triangular structure in our algebra. This is the quasi-triangular structure given in here. And when you make the deformation of this double byproduct, then we can observe that OQN is exactly this deformation. Okay. To show this, we have to use the other way to the isomorphism. It's very important to use the transport the structure. It's very important to use the isomorphism between the two descriptions of the double byproduct. Here we have a description of the double byproduct. This is a description of as a product in the tensor category. Okay. Okay. The last one is that we can also stay in a particular case only part what is the quasi-Frobenius-Lustig-Kenneth introduced by Ettinghoff and Van Oosteyen, Liu, and others. Okay, that's all. Thank you. one question. What about quantum groups? Group Q, SL2, for example, we can list it as example here? Yeah, the small one. Yeah. Yeah. Mm-hmm. Yeah, it's included, well, not necessarily the quasi. No, you will obtain the quasi one. But then the only extension we know is the extension obtained by the general case by Liu and Van Oosterheyjen and Zhang, and the other one by the thing called Jalak. This is part of them. We want, look in the infinite family, we obtain really an infinite one, because the construction is for any family in general, and then we can obtain infinite quasi-Hopf algebras, or more general. You can specify, obtain by quotient, you can obtain all of the Hopf algebras. Quasi-Hopf algebras. Last chance to ask question, to comment. If not, let the speaker again and always